Okay, good morning, Astronomy 1020. Welcome to our second week of lecture. Today is lecture 3 in lab 3, and today we're going to be doing homework 2. I suppose we'll do it live, although I would like, at some point, I might want to farm this out to the videos if it keeps going this way. Let's mess with it today and see what happens. I do owe you guys, I need to finish grading your homeworks. And an important announcement that I'd like to make is that anyone who has not turned in a homework or a lab at this point will be dropped from the class as a no-show. I actually should have gotten that done yesterday, but I was traveling late. So I'll see if I can catch up on that just after class today. Why don't we get into it? Today's assignment, homework 2, is a series of questions from different chapters. We can find it over here in the homework tab. Let's see if we can get those numbers down. Where are we? Board looks reasonably clean. So let's remember these questions: 59, 41, 43, 53, 54. Actually, I'm going to change the lighting here. Okay. Let's get your name.
Professor, just as a heads up, the homework questions are currently hidden for us students, so you may want to make them available before continuing.
Oh, right. I did that for the 10. Wow. Thank you so much, Ryan. I actually did think to do that for the Astronomy 1010 class before I realized it was Tuesday and not Monday. Sorry about that. And let's do that for the lab as well while we're at it. I've made lab 3 available and lab 4 available. Okay, Ryan, good call. Good call. This cannot be my best black marker. I definitely must have another one of these somewhere. Wow, okay. Not my finest day here today. So this is homework number 2. We have a question from chapter 2, a question from chapter S1, and a question from chapter 3. I've already forgotten them. Let's see. Okay. Question 59 from S1 4143. From chapter 3, 53, 54. Ryan Spavold, since you're so helpful, could you help us read the first question?
Just need to zoom in on it. 59, eclipse conditions. The moon's precise equatorial diameter is 3,476 kilometers, and its orbital distance from Earth varies between 356,400 and 406,700 kilometers. The sun's diameter is 1,390,000 kilometers, and its distance from the Earth ranges between 147.5 and 152.6 million kilometers.
Wait, million or thousand? Million.
Million.
Right, it's an AU. Okay, sorry.
A. Find the moon's angular size at its minimum and maximum distance from the Earth. B. Find the sun's angular size at its minimum and maximum distance from Earth. And C. Based on your answers from part A and B, is it possible to have a total solar eclipse when the moon and the sun are both at their maximum distance? Explain.
Okay, so we're trying to figure out when certain types of eclipses are possible, in particular a total solar eclipse. We've been given the diameters of the sun and moon. That's the top line. Then we've been given the nearest and farthest distances between the sun and moon. I'm sorry, between the sun and Earth and the moon and Earth. Notice that this problem has a lot of data. It has a lot of givens. And as I mentioned in homework 1, I find it to be a wise idea to extract all of your givens right onto the page. So I think it would be great if you guys could set it up like that. Let's give Ryan a second to catch up here. Can everyone confirm that I got the right numbers? I'll just take that as a big fat yes, I suppose. Our job in part A is to calculate the angular size of the moon. Notice my good formatting. I've labeled part A, I've talked about the moon, and we're going to find theta, which is angular size. I gave you a formula to solve for angular size. Do you guys remember what it was last class? I've got a vocal fry this morning.
Was that theta times d times 2 pi over 360 degrees?
That is the formula we want to use. That's the small angle formula. But I helped you rearrange it algebraically to solve for angular size. It should be right next to that formula, Sage, in your notes. Why do I remember what happened? I'm the last.
No, I remember. I just I only had my homework in there, not my notes. I just need 1 second. I'm sorry.
Amateur hour. Ryan, Dick?
Yeah. It's theta equals 360 degrees divided by 2 pi times size divided by d.
Okay. I'm going to hide Brandon the troll. Let's try to understand what's going on here for the benefit of anyone who doesn't get it. The moon has a closest approach to Earth and a farthest approach to Earth. If you guys remember, we talked about the Earth. When Earth orbits the sun, its closest approach is called perihelion. Its farthest distance from the sun is called aphelion. The moon has some similar terms. Perigee and apogee are the names for Earth. The moon, sorry, wow. Perigee and apogee are the names of the moon's closest and farthest approach from Earth. Now, the moon's orbit is pretty circular, and the Earth's orbit is pretty circular. So this picture is a little bit of an exaggeration. But, oh, actually, this kind of explains the whole thing. Function or control plus. Yeah. The moon is going to change its distance from Earth by a tiny amount. If you remember our discussion of angular size, the angular size of an object is based on its diameter and its distance. The diameter of the moon and the diameter of the sun are not going to change. They're going to stay fixed. But as the moon gets a little bit closer to Earth and a little bit farther from Earth, we might expect its angular size to change a tiny bit, which means I lied to you when I told you that the moon's angular size was, what did I tell you the angular size of the moon was in our lecture?
Wasn't it 0.5?
0.5 what?
Correctly? 0.5 arc seconds?
Nope.
No, arc minutes.
Nope.
Oh, no.
See,
Plus degrees.
0.5 degrees.
0.5 degrees.
Okay. Well, you remembered half of it anyway, Ryan, but the units, it turns out, matter. So Ryan, it cannot be true that the moon's angular size is always 0.5 degrees. Or rather, it can only be true to like one significant figure. To 2 or 3 or even more significant figures, what should happen to the angular size of the moon when it gets to perigee? How would it change?
Shouldn't it like become, it should be bigger because it would,
Yep, because
would-
closer objects should have a
Yep.
larger angular size. And so we expect that the 0.5 degrees will vary a bit from perigee to apogee. Likewise, the moon, the Earth also experiences a closest and farthest approach. Therefore, the angular size of the sun should change by a tiny bit from half a degree. Our job is to investigate those numbers. Okay, let's start with the angular size of the moon. Ryan Dick has provided us with the formula. Which does S represent and which does D represent? What are S and D representing in this formula?
I think S is size. And D would be distance.
That's right. So let's start off with the moon's perigee. For perigee, the angular size will be 360 degrees over 2 pi. The size of the moon is 3476 kilometers. The perigee is the closest approach, 400 kilometers. I want you guys to be really careful here when you plug this in. Sage, you're going to be using the Casio FX260 Solar, right? Okay. I don't want you putting in your bullshit parentheses on us today. We don't need parentheses if we just use good order of operations and the associative rule of multiplication. We're going to do 360 degrees. We will divide by 2. Then we will divide by pi. Then we will multiply by this and divide by that. Here's me doing it. 360, divide by 2, divide by pi, times 3476, divide by 356, 400. Equals. Okay, let's ask our resident math expert, Sage. How many significant figures will we be keeping in this calculation?
I believe, I didn't get to write the whole thing down. I believe 4, if I'm remembering correctly.
You believe what?
Yeah, I was going to say 4.
We've got 4 up top. We've got 4 down the bottom. These don't count for precision. Very good. So tell me what to write.
So let's go with 550 or 558.8
What the shit are you
times
talking about?
-3.
This number is not greater than 1.
Oh, I was putting it to a -3rd, but 0.5588 then.
Yeah. Always put leading zeros out front, Sage. People are notoriously sloppy in their handwriting, and they're sloppy about decimal points. If you write 0.5588 and the units?
That would be degrees.
Right, kilometers cancel top and bottom. Okay, always, Sage, when you write math in my class, If it's less than 1, always put the leading 0 out front. Unless
Okay.
you're doing it in scientific notation, of course.
Yeah.
And box that answer, it's a classy move. Okay. For our next step, we're going to do the apogee, the farthest distance. And the formula is exactly the same, but this time we change the distance. 360 over 2 pi. The diameter doesn't change. That's still 3476 kilometers. But now we're at 406,700. This time you guys punch it in and tell me what you get. Try to cut down that glare a bit. What'd you get?
I got 0.48797 degrees.
Okay, I like it. Everyone else can confirm that, I hope. You did round appropriately, did you not, Ryan?
Yes, I did.
Awesome. You rule. Okay, let's move on to part B. We're going to do the same thing this time for the sun. I'm going to save myself a little bit of trouble here. Do part B. Now, for the sun, the closest and farthest approaches, let's use our fancy vocab, are perihelion and aphelion. And this time we're going to change the distance and the diameter. The diameter of the sun is 1.39 million kilometers. That'll be the same for both cases. The closest approach, the perihelion, 147.5 million kilometers. And then the farthest distance is 152.6 million kilometers, if I remember correctly. Why don't you guys punch both of those up and get me an answer? Hopefully you can read all that nonsense. Where is that glare coming from? Is it the window or is it the computer? It's the window. Oh. Japanese screen helps a little bit. Okay. Guys, do you have numbers for me?
For the perihelion, I got 0.59 or 0.5399.
How many sig figs should we keep in this case?
Oh, 3. So 0.40, 0.540.
0.540. Yeah, we have less limiting precision here. So this should be 0.540. Nicely done. And for aphelion?
0.522.
Nice. 0.522. So we can see the angular size of the sun and moon to one significant figure is half a degree, but there's tiny variations happening at the hundredths place. Ryan, Dick, and Sage, let me know when you're done, so I can go on to part C. Ryan?
Almost set.
All right. Part C, Ryan's babbled. What does it say?
Part C is based on your answers to part A and B. Is it possible to have a total solar eclipse when the moon and sun are both at their maximum distance? Explain.
Okay. Let's review the angular size of the moon at maximum distance. But this time, let's round it back to 2 sig figs for the sake of sanity. What's the moon's angular size at max distance at apogee to 2 sig figs?
0.49 degrees. Sorry.
And what's the angular size of the sun to 2 significant figures?
0.52 degrees.
Can we have a total solar eclipse? No. Why not, Sage?
The sun is 0.03 degrees larger than the
Right.
moon.
Let's draw that picture. So if this is the sun, the disk of the moon will not fully cover the disk of the sun when they're both close to their maximum distance. It turns out that you get this type of an eclipse if you're anywhere within 8 days of the moon's apogee, okay? If you're within 8 days of the moon's apogee during a solar eclipse. So this would be the sun. Disk of the sun is 0.52 degrees. And the moon, internal to that, is 0. What type of eclipse is this called? Do you guys remember?
An angular eclipse.
An annular eclipse, good. No, a total solar eclipse is not possible at max distance because the angular size of the moon, I like the way Sage put it, is 0.03 degrees less than the disk of the sun. And you can mention that instead you get an annular eclipse. I don't really have room to write a full sentence, so I'm just going to put annular eclipse underneath. You can do so as well. Sorry about my crappy handwriting. I'm not doing good today. I don't have a good brain.
Actually, sorry about my crappy handwriting.
What's that, Sage?
I was like, actually, sorry about my crappy handwriting.
Oh, yeah. I'd really like to see if I can fix my screw up last night. I'd like to see if I could get your grades somehow done before lecture during the little gap there. That's going to require us to move quickly. So I'm going to cross this off and we're going to move ahead. Sage, get ready to read chapter S1, number 41, please. Okay. This is a really big problem, but slow and steady wins the race. Sage, can you read S141?
So fundamentals of your local sky. Answer each of the following for your latitude. A is, where is the north or south celestial pole in your sky?
Let's just stop there. Do you guys remember the latitude for Rhode Island? What is Rhode Island's latitude? Look it up in your notes if you can't remember it. Or use your compass app.
Of 41 degrees? Or is that longitude? I forget.
No, it's 41, it's 42 degrees north.
42 degrees north? Okay.
At least it is in Providence, where I'm recording this. Okay. And don't forget, you have to have the north part too, right? Yeah. 41 degrees and 49 arc seconds. I don't know if you can read this. No, it's too fuzzed up. 41 degrees and 49 arc seconds rounds up to 42 degrees. Okay, so the first question asks us, where is the north celestial pole? You know what? There's a little game that we should have played. Here's a picture of, oops. What the hell? Here's a picture of your local sky in slide 50. This is what your local sky looks like. The north celestial pole is right here. How are we going to describe the location of that? Which coordinate system should we use? That's the point, oops, on your sky that represents the north celestial pole right there, the blue dot.
Do we want to find Polaris with the geographical coordinates?
Well, geographical coordinates give you your position on Earth.
Oh,
Polaris
okay.
is on the sky, so that
So
probably.
the horizon system.
Let's try the horizon system. And what are our two angles?
42 and 71.
That's our geographical coordinates. I'm asking, what are the names of the angles that we use in the horizon system?
Oh, the altitude and azimuth.
Okay, so what is the altitude here? Altitude is defined as your degrees above the horizon, right?
Mhm.
So from here up to here,
Would be 45.
not 45. To see this, I might want to use the whiteboard here. This can be a little tricky. Let me start by drawing Earth as a big circle, okay? And let me see if I can draw a couple of lines to help here. Oops, I want to undo that. Let's make a black line. Okay, let's imagine that, what the hell? Let's imagine that the North Pole is oriented like so. And that you're a little dude, a little pink dude, standing here. Oops, I guess you're black and white at the top of Earth, okay? You're about halfway up from the equator. The equator is like perpendicular to the North and South Pole, right?
Mhm.
And you're at some angle up. All right, let me try. Can I move the little dude? Can I move the little dude? No. Undo that. Oh, I moved his head.
Viva la revolution.
How do I move the whole little dude? Oh, okay. I got an idea. Let's take the eraser. Let's just erase the little dude. Okay. Let's try drawing the dude again, this time better. Okay. You're a dude that's here. And of course, right, if your latitude is 42 degrees, that means if this is the equator, your latitude is your degrees north of the equator, right?
Oh, okay.
So now let's try to draw, I wish I could draw a semicircle here. Can I draw a circle? This is going to be our local sky. Let's undo that. I wonder if I could erase part of the circle. That would be pretty dope. So let's take the erase. Oh, no. Okay.
Hmm.
I'm just trying to figure out how to represent this. So this will be our horizon. I should have just done this on the board. This will be our zenith here. Okay.
Mhm.
And here's like north. And here's south. Okay. Your head points in the direction of the zenith, right?
Mhm.
And the equator points in the direction of the celestial equator. So your celestial equator is like here, okay? That's your CE. Your Polaris, your north celestial pole, is perpendicular to the equator in that direction,
Mhm.
right? This is, wow. Okay, I'm not very elegant with this. I'm faster on the chalkboard.
Okay.
I think this would have been better if I just drew it out, but I wanted to save the stuff behind me there. Okay, so if the angle between the equator and the dude's feet is 42 degrees, what can we say about the diagram here of our local sky? And by the way, you should ignore all of this. This is all stuff that's not visible on your horizon, right?
Mhm.
So ignore all of that. I couldn't figure out how to draw this better. What do you think in math, Sage?
I think I lagged out during your question.
Oh, shoot.
Yeah, I'm sorry.
We have to find the this is a geometry problem.
Yeah, that
We-
much.
We need to find the altitude of the North Celestial Pole.
Okay. Those angles wouldn't be the same, would they?
What angles?
The.
There's
do you want
lots
me
of
to
angles.
say- Which, yeah, I'm sorry, the two on the very outer edges, the between S and CE and NCP and N. No, I'm sorry.
Hold on,
42 degrees north, no.
So this, I'm not sure exactly what you're saying, but this angle is not going to be the same as that angle, if that's what you're
Okay.
saying.
Yeah.
It is true that this is a 90-degree angle. If that's true, the sum of these outer angles should also equal 90.
But the CE or NCP are different. I got that.
Which of these angles do we know for sure? 1, 2, 3, 4. One of these angles we know for certes. Which one is it?
Probably 4.
Well, that's the one we're trying to get.
Oh. Mhm.
All we know is our latitude, this angle.
And the equator points towards the celestial equator, so probably.
And your head points towards your zenith.
Yeah, probably 2.
Yes, and what is 2?
42.
Right, because the angle between the celestial equator and the zenith is the same as the angle between the equator and your feet, and our latitude is 42 degrees. So you know that this is 42 degrees. So what does that make angle number 3?
That would be 48 degrees.
Because the celestial equator and the north celestial pole have to be at 90 degrees with respect to each other, right?
Mhm.
Okay. So what's angle number 4 then?
Also 42.
Yeah, because the zenith and the horizon have to have a right angle. So therefore, we know that the altitude of the north celestial pole is the same as our latitude. It's 42 degrees, right?
Gotcha.
Now, believe it or not, that's only, oh shoot, I didn't mean to do that. Okay, so if we're going to use the horizon system, we need an altitude and an azimuth. Which angle did we just figure out?
The altitude.
And the altitude is 42 degrees, same as our latitude. What about the azimuth? Now you got to remember what azimuth means, and you forgot. So
It's the degrees along the horizon.
you're missing
clockwise
something.
north. So
Oh, can you say that one more time, loud and
The-
proud?
degrees along the horizon measured clockwise from north.
Okay, cool. So we have to find the closest point on the horizon, which if the north celestial pole is there, the closest point on the horizon is there. How many degrees clockwise from north is that?
0.
Right.
Yeah.
This is going to sound hard to believe, but the direction of the north celestial pole is north. Its azimuth is 0. All right.
That makes
We
sense.
can use either 0 degrees or north for azimuth. Geez, hopefully the rest of this goes faster. Part B. You know what it is? I had a series of sample problems to do using the horizon system, but I couldn't get to them last class because I needed to get to equatorial coordinates. So even though you've had enough information to solve these problems, some practice would have helped beforehand. Welcome to life. Okay, what's question B, Sage?
Question B is going to be, describe the meridian in your sky specifying at least 3 distinct points along it, such as the points at which it meets your horizon and its highest point.
Okay, the meridian is not a single point like the North Celestial Pole. The meridian is an arc that goes through your sky. You probably forgot what it is, but it's the arc that goes like this from north to south through the zenith, all right? Whenever you have to describe an arc in your local sky, a single point will not suffice. A better idea is to use a set of 3 points. I like to choose the point where the meridian rises, the reach, which is the highest point it makes in your sky, and then the set point. In other words, these 3 blue dots here, okay? Let's format it. there will be a rise, a reach, and a set point. But each of those points will have their own altitude and azimuth associated with them. To do this job right, we're going to need like 6 numbers. This sounds like a great job for you guys who are practicing. Let's start with the rise. We need an altitude and an azimuth for this point here. Who can do that? Ryan, Dick, you want to try?
Yeah, would that be 0 degrees?
Which are you giving me, altitude or azimuth?
Altitude.
Okay, I agree. The altitude of that point is 0 degrees because you are no degrees above the horizon, right? You're on the horizon, so your altitude is 0 degrees. What about your azimuth?
Would that be east?
Does that blue dot look like east to you?
Or north?
What's the azimuth of north?
0 degrees.
That's right. So the altitude is 0 degrees. And the azimuth is 0 degrees or north. And we can express both of these at once by using the term due north. Due north means on your horizon. Okay, now someone try to give me the reach point.
Would that be 90 degrees for altitude and
You are correct. It would be 90 degrees altitude. What about the azimuth of your zenith?
would it also be 90 degrees west?
Not exactly.
Not exactly. Okay.
Remember, Ryan, that the azimuth is your degrees from north to the nearest point on the horizon. But
Okay, so it'll be 270 degrees then.
not
or-
exactly either.
Oh,
If you're at the zenith, what is the closest point along the horizon?
uh, uh, I'm not sure. I'm trying to.
Sage, do you know?
Aren't they all equidistant?
They are. What does that mean about the azimuth of the zenith?
It's the center.
It's what?
The center. Or the oh, I'm sorry, the azimuth. I don't know. Would that be 180?
No, 180 is south. The
See,
southern
that's what I
horizon is no
figured.
closer, huh?
That's what I had for the next one, but I was like, I can't figure out where that exactly would be if it was like 0.
That's because it's well, it's not that it's a trick question. The azimuth of the zenith is multi-valued. Every single point along the horizon is equidistant from the zenith. That makes it undefined, or what we say in mathematics is degenerate. This is a degenerate point because no spot along the horizon can claim that it's closer to the zenith than any other. That's okay because the altitude specifies a unique spot. So we'll say 90 degrees altitude. We will leave the azimuth dashed because it's undefined, but we can throw in if we want at the zenith because it's a unique point on the celestial sphere. Watch out for that. There's always 2 coordinates in any curved coordinate system that are degenerate. There's some kind of highfalutin mathematical theorem about that. I can't remember what it's called though. And how about the set point?
Is that going to be 0 degrees altitude and 180 degrees azimuth?
Very good. It's on the southern horizon, so it has no altitude and 180 degrees azimuth or south, and that's what we call due south. Okay. Sage, when you have that down, read us part C.
Describe the celestial equator in your sky, specifying at least 3 distinct points along it.
Okay. This is going to be a little trickier. Actually, maybe not so much. Like the meridian before us, the celestial equator is an arc that runs through your sky. So we will need 3 points to describe its trajectory: the rise, the reach, and the set. For each one, we require an altitude and an azimuth. Let's see if you guys can follow me here. Of course, in my diagram of my local sky, this red arch or this arc represents the celestial equator. The 3 points, if we consider the celestial equator to go in the same direction as stars go, the rise point will be here, the highest point it reaches will be there, and the set point will be there. Let's begin with the, trying to find a non-threatening color. Let's begin with the rise point, which is here. What is the altitude and azimuth of that point?
Zero degrees as 0 degrees altitude and 90 degrees for azimuth.
Excellent. It's on the horizon, so it's 0 degrees in altitude, and clockwise from north, it's 90 degrees or east. Remember that azimuth is kind of the same thing as direction, all right? So 0 degrees altitude, 90 degrees azimuth or east. I would accept east in place of that. And of course, since it's on the horizon, we could say that 0 degrees east is due east. How about the reach? This one's interesting. The reach is this point right here. What is the altitude of that point? What is the azimuth of that point? This is the altitude. It's your degrees above the horizon, right?
Would that be 48 degrees?
That's right. In our previous question, we saw that the angle between the celestial equator and the zenith, this angle here was our latitude, 42 degrees. So if this is 42 degrees from there to there, if this is a 90-degree angle, that should be 48 degrees. And what about the azimuth? The azimuth, Ryan Dick, would be that point there. What would the azimuth of that be?
0 degrees or 180 degrees?
Which is it?
180 degrees?
Right. 0 degrees starts north, and then it swivels clockwise from north. Half a circle is 180 degrees. So we have a reach of 48 degrees at 180 degrees or south. And the set point, students? over here. Let's do this quick.
0 degrees altitude and 270 azimuth.
Beautiful. And that's the same thing as due west. We could say this in a kind of literary way. We could say the celestial equator rises due east, reaches an altitude of 48 degrees in the south, and sets due west. That's a kind of classy way to say it that uses all of the specificity and power of the horizon system. This is how an astronomer talks. This is how someone who knows how to describe things in the sky should talk. That's what we're learning how to do, okay? All right. If you got this, I'm going to ask Sage to read us number D.
Does the sun ever appear at your zenith? If so, when? If not, why not?
Okay. To do this question, there's a little trick here, okay? Let me see if I can make a quick and dirty local sky using this Frisbee here. I should have done this in the previous problems instead of trying to use that whiteboard feature. It's too clumsy. So here's a quick local sky that I'm making with you guys, north to south. Our zenith is here. The observer stands at the center of the field. And you guys will remember that we have a north celestial pole that's about 42 degrees up. I could have done that better. So our north celestial pole is 42 degrees in altitude. And our celestial equator is about 48 degrees from the south. This is a quick and dirty model of our local sky. Okay, let's look at the relationship between the sun and the celestial equator. You will recall that the sun travels the path of the ecliptic over the course of the year. The sun is on the celestial equator at the spring equinox. The sun will get higher and higher in the sky until it's 23.5 degrees above the celestial equator at the summer solstice. It'll return back to the celestial equator on the fall equinox, and it'll drop below the celestial equator by 23.5 degrees in the winter solstice. Now, what that will look like from a perspective of your local sky is it's going to look something like this. The path of the sun on either of the two equinoxes, and let's just put a little sun here. On the spring equinox, the sun should rise due east, because remember, on the spring equinox, the sun should travel the celestial equator, right? So the sun is going to rise due east. It's going to come up and cross your meridian at the celestial equator at 48 degrees in the south, and it will sink back down in the west, due west. Each day after that, if it heads towards summer, each day it's going to travel the ecliptic and be a little bit higher. So a day afterwards, it's going to come up here and do that. And a day after that, it's going to kind of come up here and do that. And then finally, it'll get to a maximum displacement of 23.5 degrees above the east. It'll rise north of east on the summer solstice. It'll come up to some maximum height, which is 23.5 degrees above your celestial equator, and it will set in the south. Does the sun ever reach the zenith? Why not? Not in Rhode Island anyways. Why not in Rhode Island?
We are more than 23 degrees with our between the Our difference between the celestial equator and the zenith is more than 23 degrees. So in its
That's an elegant way to put it,
differences.
Sage, and I
Yeah.
like it. Another elegant way to put it is we're too far north of the tropics. Like, for instance,
Yes.
we know that this angle here is 48 degrees. That's the angle to our celestial equator, right? I'll go over that again during lecture today. So what should the maximum altitude that the sun could ever reach, say at noon on the summer solstice?
Like 81 and a half.
71. It's 48 plus
Oh,
22.5.
I'm sorry. Yeah.
That's okay. You were doing it quick in your head. I do that stuff all the time. Okay, all right. So basically, you've got the right idea. The sun can only get 23.5 degrees above the equator, right? So the maximum altitude of the sun would be like up here somewhere. And any other day, it's going to be lower than that. So we should write, no, the sun will never reach the zenith in the Rhode Island local sky but only a maximum altitude of, we'll actually spell it out so we can remember how Sage got all that. The maximum altitude of the sun will be 48 degrees plus 23.5 degrees equals 71.5 degrees south at noon on the summer solstice. I hope that makes sense to you guys. So in other words, the maximum altitude the sun will ever get is 23.5 degrees above the celestial equator. And as Sage eloquently put it, since our latitude is greater than 23.5, we can't have that. In fact, the latitude of 23.5 degrees north on Earth is called the Tropic of Cancer, right? The Tropic of Cancer and the Tropic of Capricorn define the tropics. The tropics are places where the sun can reach the zenith in the local sky, if you think about it that way. All right, now I need us to read part E. Or I need Sage to read part E, rather.
It's just finding my button. What range of declinations makes a star circumpolar in your sky?
Okay. Range of declinations that are circumpolar. I talked about circumpolar stars last class, but not extensively. Does anyone remember what circumpolar means?
There are stars that never set. Because they're
That's
too close to Polaris in the
Right.
local sky.
and just to remind the rest of the studio audience, I had some kind of groovy pictures here. Oh, wow, sorry. Circumpolar stars are stars like this star, which they don't sink below the horizon because they're too close to Polaris. Now we have to find the range of declinations that are circumpolar. And this is going to be tricky for you guys. So we have to kind of, let me show you a picture here. Don't forget that a range means two numbers. And circumpolar stars are going to be up here near this purple ring. Do you guys remember how we define declination? How do we define declination?
Mine says latitude, degrees measured in positive or negative from the celestial equator.
Right. So where's the celestial equator in this picture? Trying to get rid of the mess here. Where's the celestial equator?
It's that red one,
Right. And what would the declination of that red circle be?
0.
Good. Allow me to I'm just trying to clean up this diagram so I can write all over it. Okay, so this is 0 degrees here, right? Let's see here. Oops. What's the declination of the north celestial pole?
$90.
That's
Actually,
right.
Oh, it was? Oh.
Yeah, but it's positive 90, right? Okay. Is Polaris circumpolar? Right.
Yes, it is.
So remember, class, a range. Oh, I should have saved that. A range is 2 numbers. It goes from a low value, the declinations go between that and a high value. We know that Polaris at the North Celestial Pole is a circumpolar star at positive 90 degrees. There can be no higher declination than positive 90. So we know that the range of circumpolar stars should go from some low bound to some upper bound. At the highest possible circumpolar star, the highest declination that can be circumpolar is Polaris at positive 90. What we really need to do is find the lowest declination circumpolar star. And to do that, I want to show you a picture at the beginning of our book, chapter 2. It would be nice if I could find a picture of it. Caps stars over the grand arches. There's a cool picture, and I don't know if I'll be able to find it. In the first opening part of our book, someone went to the Grand Arches National Monument in Utah, and they took a picture of circumpolar stars as seen through the Grand Arch. And it was just a really nice photograph. It wasn't quite this one. Bloody hell. But you know what the best way to do this would probably be, the fastest way, is for me to just take up the book and then adjust my focus appropriately. So let's see if I can do that. I've got the book here. And I think the opening chapter, the opening photograph from chapter 2 is kind of lovely. So I'll share it with you. This kind of works better when we're all hanging out in person, but let me see if I can adjust the focus there. They've got the Grand Arches National Monument. Yeah. And some clever bastard has taken a photograph so that you can see circumpolar stars with Polaris right through the arch there. It's kind of cool. Now, what is the last star that is circumpolar? This is really instructive for another reason. Look at this photo and ask yourself, the last circumpolar star is which star in this photograph?
It has to be Polaris, right?
No, Polaris is the most circumpolar star.
Oh, the last. Oh, okay.
Like, in other words,
Like the last. Yeah.
let me undo my focus here, 65. In other words, Polaris is circumpolar, right? And forgive how small the diagram is. These stars surrounding Polaris are all circumpolar. What can we say about the very last circumpolar star, the lowest circumpolar star? Look at the picture and then answer the question. Where is the last circumpolar star in this picture?
At the zenith? Question mark?
No,
No.
not at the zenith. Look at the picture.
At the, I don't know.
Is this star circumpolar?
Yes.
Is this star circumpolar?
No.
Okay,
it's
so you already
far.
understand that much. So what's the last
Okay.
circumpolar star? It's the one that does what?
Skips the horizon.
In
Stays
which
the
direction?
arc.
It grazes the horizon in which direction?
Clockwise.
No. Like west, south, east, west
South.
direction. Which direction is this?
That's south. East, west.
They call Polaris the North Star.
All of the one that I did not say. Yeah.
Fucking north, because that's the North Star, right?
hmm
So in other words, Sage, what you meant to say was the last circumpolar star is the one that grazes the horizon in the direction north, correct?
Got you.
Okay. So the question then, Sage, here's that circumpolar star here. The last circumpolar star is the one that's going to cut through your northern horizon, right there. Here we go, Sage. What is the declination of your northern horizon? Let me help you. Okay, hold on. You can do this. You can do this. You know that the celestial, oh shoot, I blacked all that out for nothing. Wait, maybe I could do it in a different way. Let's take a big fat line of dark stuff. Oh yeah. Oh, okay. Sorry. I just want to clean this up a little bit. Okay. Damn it. Okay. What? Okay, I'm failing at drawing in life all at the same time. So let me just scribble this. You know the declination of the celestial equator is 0 degrees.
Yep.
And you know that the declination of the north celestial pole is positive 90 degrees. What's the
Yep.
declination of your zenith, Sage?
That would be 42.
Positive 42 degrees.
Yeah.
Well, yeah, because that's your latitude, right? And this angle here from, oh, this is getting messy. From here to here is 42, right?
Or yeah.
What would the declination of your northern horizon be? Define
40.
declination for me.
Or 130.
Someone define declination.
Degrees positive or negative measured from the celestial equator.
Awesome.
Cool.
So how many degrees positive or negative is that from the celestial equator?
Either 48 or 138.
There's no such thing as a declination of 138.
So 48.
False. Oh, wait, no, sorry, correct. Wow, sorry. If this angle, my brother, from here, your declination, I should use a different color. Let's use orange. The declination of your northern horizon is the angle from the celestial equator up. You know that this angle from the previous questions is 42 degrees, correct? So the angle from the celestial equator up to north has to be 48 because there's a 90-degree angle between the north celestial pole and the celestial equator. That's kind of tricky. The book has a little blurb on this, but no one reads the book, so what do you expect? So the range of declinations is from positive 48 degrees to positive 90 degrees. Those are the stars that will be circumpolar in your local sky. How about part F?
Let's see. What is the range of declinations for stars that you can never see in your sky?
All right, I have a nickname. I call these anti-circumpolar stars.
Anti-circumpolar.
We want a range of declinations that are anti-circumpolar. Circumpolar. I don't know if other astronomers do that or if that's just me, but it seems like a pretty good name for these stars. We're going to lay this out the same way that we did the last one, from low to high declinations. Obviously, kids, if you're standing in Rhode Island, there are some stars that never come up over your horizon. Let's take a simple one. The South Celestial Pole doesn't really have a star at it, but if there was a star at the South Celestial Pole, you wouldn't freaking see it anyways, because it would just sort of be pinned to the sky below your horizon. There's also a whole bunch of circles, you can see them here, of like anti-circumpolar stars, like this yellow ring. If a star had the yellow ring's declination, it would never be able to come up above our local sky. From the diagram, it looks like the anti-circumpolar stars will have a range of declinations that starts out here at the South Celestial Pole. And by analogy with the previous question, they will orbit on rings that come up to and just barely graze your southern horizon. Therefore, the range of declinations for anti-circumpolar stars should be from like here up to here. Can you guys look at that diagram and tell me what the range of declinations of anti-circumpolar stars are? What's the declination here at the South Celestial Pole?
They would,
That,
oh,
no, you go ahead.
that would be negative 90 degrees, and then the other one would be negative 48.
Very
Degrees.
good. That's negative 48 because it's 48 degrees off from the celestial equator. I think both Ryans, who have had some of this stuff in my 1010 course, will attest to the fact that your first time you learn this, it's pretty fucking confusing, right, guys? But that the second time around, it seems like you guys are digesting the logic of it a little better. Would you agree with that statement, or would you say that I'm not making sense there?
Yeah, I agree with that, because there are times where I just wanted to look back in my own notes, but I knew because I just didn't understand this the first time I was going through this, but it makes a lot more sense now.
Yeah, I noticed that you were pretty quick to give those answers. That's not the way a person learning it for the first time would do it. And so that's hopeful, because Ryans can attest to everyone that this stuff is a little goofy first time around. But you really have to kind of work at it to get it, all right? So our lowest declination would be negative 90 degrees, and the highest would be negative 48 degrees. There's also some stuff on that in the books as well. Okay, there's no doubt about it. That was an epic and very difficult question. That's why I asked it. This homework kind of sucks, I'm not gonna lie. We're already at 131. I might actually save the last two problems and do them during the lecture. Let's see how bad this next one is, number 43. Sage, I'm going to erase, okay? Everyone erase. Ryan, Dick, would you read us chapter S1, number 43? Ryan, Dick, did you hear me? I just want to get some feedback from you here.
My mic was muted.
Oh, okay.
The local path of the local path of the sun. Describe the path of the sun through your local sky for each of the following days. 8th March and September equinoxes.
All right, let's start there. The path of your sun is a path like any other star. There's a rise, a reach, and a set. And we need an altitude and an azimuth for both, or for all three rather. I will remind you that on the equinoxes, the sun travels the path of the celestial equator on that day. In other words, remind yourself that each day the sun is pinned to the sky, kind of like pin the tail on the donkey, and the sun will just travel a path of constant declination on that day. On the equinoxes, the sun is kind of stuck to the celestial equator, and it will do this, right? On some other day, it will be stuck to some other ring that's either above or below the celestial equator. In fact, it might be better for you guys if I change the underlying diagram. Can I do that? This might be the better diagram. Function F5, 9. Okay. So guys, I need a rise, a reach, and a set for the spring or fall equinox. Can you give that all to me? Same as the celestial equator. Sage, you're muted.
The altitude for the rise and set are going to be 0.
You know that. If they rise and
Yeah.
set, the altitude has to be 0. Okay, I like your moves. Let's use direction instead of azimuth. What's the direction of sunrise on the spring equinox? Just look at the fucking thing.
Yeah, that's going to be east. I was just trying to put it into degrees. I think that's 90.
Yeah, that's okay though. Let's just use direction right now. I want you guys to just kind of burn into your brain that azimuth is the same thing as direction. So it's 0 degrees east. What's the reach? Oh, sorry. What's the set azimuth, Sage?
Oh, that's going to be west.
Yeah. Okay, what about the reach? What's the highest point and the direction that the sun will reach on the spring equinox at noon? Up here. What's that
The
angle?
degree we have for the celestial equator, probably.
Well, we need an altitude. So what's the altitude is the degrees from here to there.
Yeah,
That's the altitude.
that's going to be 48.
Very good. And what's the direction?
South.
Good. So it reaches 48 degrees in the south. In other words, it's the same as the celestial equator that we described in the last problem, right? Because you're on the spring or fall equinox. What's part B, Ryan Dick?
The June solstice.
Okay. Altitude, azimuth. Best I can do here. Rise, reach, set. Okay, actually, well, I'll just lower this time. I should be using a ruler for these, but I'm going kind of quick here. All right. Let's get our math friends to help us out with this. Sage, you were pretty quick for this last time. When the sun's rising, it's going to be here on this ring. What's the altitude of the rise point?
That's going to be 0.
Okay. So if I pause the share, can you guys see the board now? What are you guys seeing right now?
The PowerPoint.
Oh. There's some shit. Okay, I thought if I hit pause share, you'd see the board, but I guess I'm wrong.
There it goes.
So you know the rise is 0 degrees. What about the azimuth or the direction? This could be a little bit tricky. That's why I wanted our resident math expert to see if he could understand the problem.
71.5.
Hell F no. Don't confuse longitude and azimuth. The azimuth are your degrees clockwise from north.
Oh,
So that's 90 degrees. What
Yeah.
about this angle here?
is it moved by 23 or is it half?
Okay. Is it 23 or is it half? That makes no
Does-
sense.
Doesn't it waver 23.5 degrees?
Ah, but look, brother, my math-loving friends, this
Is it bisecting that angle?
this is spherical trigonometry. So what I mean by that is watch this maneuver. On a sphere, every time you traverse one point to another on a sphere, it's always an angle. This from here to here is definitely 23.5 degrees, okay? But look, Sage, if that's 23.5 degrees, let me see if I can move that.
Oh, then that's gonna be
Like more than 23.5.
yeah.
In fact, this is a problem in what we call spherical geometry.
Yeah.
If this is 23.5 degrees, this
Then-
is going to be longer. This is a triangle that's superimposed onto a circle. And Sage, you may not have ever encountered this
Yeah,
in your
it
math
is.
adventures, but you
Yeah.
actually need to use the spherical law of sines to solve this problem.
SOHCAHTOA.
No, but this ain't normal SOHCAHTOA. SOHCAHTOA is Euclidean flat geometry.
Yeah, it's just hot.
Think about this, buddy.
I don't know.
On a sphere, shit gets a little buggy.
Is it
Now-
come out to like
I should
66.5?
mention that this is over the pay grade of the class. All right, you're not supposed to be able to do this kind of stuff, but if you go, when you dissect a sphere through the center, that's called a great circle. When we're going from the equator, the celestial equator, up to 23.5, shit, this chalk, all right, like that, that's 23.5 degrees. But
Hmm.
we've got an angle that's going like this, right? And this kind of a triangle on the surface of a curved sphere is really weird. It doesn't obey Euclidean
Yep.
geometry. Think about it. Imagine if I make this triangle really small, all of these angles are not going to add up to 180. And you can see that if you go all the way up to the North Pole and go down like this, it's possible to make a triangle on a spherical surface in which all of the angles are 90 degrees, at which point they add up to 270. So
Huh.
things are really weird on the curved geometry is another level of nuttiness beyond flat tabletop geometry. If you're just a
Yeah.
regular fella or a fella-ette or whatever the crap you are, if you've taken normal high school geometry, you only dealt with tabletop planes, two-dimensional
Yeah.
surfaces. This kind of shit is something you'd encounter as a math major, or if you're a badass astronomer who has to know a little bit of everything, you got to know a wee bit of spherical geometry.
That's super crazy.
It is super crazy, and I've learned just enough of it to know that I'm not very good at it, but there is something, there's the law of sines and cosines in tabletop geometry. In spherical geometry, they have the spherical law of sines, the spherical law of cosines. Anyways, you can't be expected to do all that in an astronomy 101 class. So here's what we're going to say. We know that, yeah, this is 23.5 degrees. And we know from just kind of being smart that this is probably an angle that's a little bit bigger than 23.5 degrees. Since we know that azimuths are also kind of like directions, why don't we wuss out here? And let's say that the sun's going to rise north of east, okay? It's not going to rise due east. It's going to rise north of east by a number of degrees that's greater than 23.5, but we're not going to calculate it, okay?
Okay,
We could, but we won't.
gotcha.
So we'll say it rises north of east. Okay, help me out. The reach, I do expect you to be able to do. I expect you to be able to get the reach because the reach happens along what we call a great circle. You should know this angle from our previous question.
Positive 48.
No, positive 48 is the angle from south to the celestial equator, right?
Positive 71.5.
Yeah, because remember how we did this before for the sun at the zenith?
Yeah.
48 plus 23.5 gives you a maximum altitude of 71.5. Notice, Sage, that this is easy geometry because we're going along a curved, what we call a great circle. We're slicing through the diameter. I probably lost half the goddamn people in this class, but whatever. All right. What's the direction?
So.
Yeah. And where shall we say it sets?
0 degrees north of west.
Very good. Okay, Ryan Dick, why don't you read us part C? I'm going to repurpose this stuff here.
Yep. The December solstice.
Okay. Do you guys know what the answer is? I want to rise, reach, and set. Let's see if you're getting any better for this curve here. Rise, reach, and set. Give it to me straight.
Zero degrees for altitude.
And for azimuth,
North?
does the sun look like it's over here? That's north.
No, it's south.
The south is over here. Does it look like it's south?
Southeast?
South of east. Okay, fine. So 0 degrees south of east. The reach,
48 degrees?
false. 48 degrees is here. But at noon on the winter solstice, the sun's down here. So Ryan Dick, how many degrees is it from here to here?
23 degrees? Or 23.5?
Okay. And how many degrees is it from here up to the celestial equator?
71.5?
No, 71 is up to the summer solstice. The celestial equator is not at 71.5. I'm doing this too fast for you guys. That's the problem. What is the altitude of your celestial equator, Ryan? You can use your previous questions to cheat.
Uh, 48 degrees.
So if this is 48,
Yep.
and that's 23.5, then what should that be? Feel free to use your calculator.
25 degrees?
You're subtracting 23.5. I mean, close. Just do 48 minus 23.5.
24.5 degrees.
Thank you. There's no reason not to have that extra precision.
Yep.
So 24.5 degrees. And then what about the set?
0 degrees.
Altitude and
Uh,
direction?
south or southwest?
South of west. I don't want to say southwest because it's not exactly 45 degrees. Okay. I'm getting a little heebie-jeebies about time. So we're going to skip the final problem, okay? So for 40, sorry, we're not going to skip the final problem. For 43, we're going to do A, B, and C only. We're going to skip D, okay? Sorry. This was, we'll skip D. I'm debating whether I want to do 53 and 54 during lecture or if I should do it now. On one hand, students watching the video later will have their homeworks done. On the other, this way they have to watch lecture to find the answer to the last two problems. That's kind of sinister. What I really want is a few minutes before class starts. And I need to teach you some BS. What to do. Okay. I am going to include the final two questions as in-class exercises during today's lecture. That's how I'm going to do it. That way we can take a break before lecture starts. I have a couple of things I want to do. What I will do for those who want to cheat, and I can't even believe I'm doing this, is maybe I'll see if I can record the timestamp at which I introduce those questions. And I'll give everyone a hint as to where to find them in the lecture. That's if I'm feeling nice. I may not. Okay. Are you guys okay with doing the final two problems during lecture? Shouldn't really matter to you, right? All right, let's take
sorry,
it.
I just got like knocked over shit and the phone call at the same time. I just got like surprised.
It's okay. I want to do a couple things before lecture starts. So let's give ourselves a good 15 minutes before we get going or so, okay? I'm going to start my timer now. See y'all in 15. Sound like a plan? All right, peace out. Okay. Welcome Astronomy 1020 to our third lecture. Today we're going to do a mishmash of things. We're going to do a bit of stuff in the local sky, just to wrap up in the local sky. We're going to learn about planetary orbits. We're going to study Kepler's laws of planetary motion. And then we kind of need to move on to talk about Newtonian gravity, some background that we need to understand how the orbits of stars work. Our lab today, first of all, our homework that we are doing, or the homework that we just did a moment ago, we only did 3 of the problems because they were long and complicated and it kind of took a while. So during our homework session today, we did 59, 41, and 43. These problems are quick and easy. We're going to include them as in-class questions during lecture 3 today. So I'll try to keep track of the time when that goes down. Next week, not next week, but on Thursday, we have a very intense homework that has to do with gravitation. And so I need to sort of get far enough into lecture today where I can actually cover some of that. That's going to be a little bit of a challenge, but it would be cool if I could do it. So let's get to it without any further ado. In our last lecture, by the way, I know there was one other announcement I wanted to make. After this class today, I'm going to verify enrollment. Anyone who did not turn in a homework or a lab or anything will probably be dropped from the course as a no-show because I haven't seen you and I haven't seen any submissions. That seems logical to me. Our lab today, we're going to make a model of a planetary orbit as an ellipse. And that lab here is a short and easy one called Planetary Orbits. I'd recommend that at some point during today's class, I know it takes a while for some of you to print, that you print this one page here, 5-5. And it looks like that's page 5 out of 6. So I'm going to do that here. I'm going to hit print pages custom, and I'm just going to print page 5. That ought to do us. It would be really cool for today's lab if you could have a few tools at your disposal. A piece of cardboard, like cut a piece of cardboard off of an old wine box, a little loop of string about 15 centimeters long or so. Oh, hello, Kathy. Welcome to our live show. And a couple of thumbtacks. I don't know if that's something that you guys think you can rustle up. Would that be doable? I know, I'm asking for a lot. Hey, Kathy, I'm glad that we have a new person joining our live class. That's very exciting. Now, Kathy, just so I know who the hell you are you Kathleen Cedarback? Is that you?
Yes.
Cool. Okay, that's great because that means you've done all your work up to now and I don't have to yell at you. Okay, cool. I'm getting spammed like crazy. Okay, I've got my lab printed. Sorry, I'm getting really distracted today. Let's try to get into this lecture. Class, pause the video for a second. I've got a small emergency, just one sec, not a big emergency. Okay, class, let's get into lecture 2 today. Once again, if at some point during this lecture, you can find 2 push pins, a loop of string about 30 centimeters long, and a piece of cardboard, that would be amazing. If not, you're gonna have to follow along with me as best you can. Especially if you don't have those materials, I believe I actually provided a copy. Did I do that? Was I cool enough to do that? No, I was not. I think I could though. I could edit this. If you don't have those tools, maybe I'll give you a copy of my ellipse. It's kind of cooler if you make your own ellipse though. That's sort of the whole point. But I would like your ellipse to look good and not crappy. Where do I have this thing? Astronomy.
Yeah,
Like a larger.
I personally would really appreciate having one because when I did this last semester, it did not work very well with what I had.
Yeah, I saw some pretty shitty ellipses, to be honest, and it horrified me. But you know, this isn't like a complicated task you have to do. It's just a loop of string and some thumbtacks. But I know I don't want to break the spirit bank of all those people at home watching TV here. So I just uploaded, Ian, a copy of my drawing that I'm going to do again for you today. It's obviously way less cooler if you use this, but if you have to, use it. Okay, it would be neat if you had a
small piece of cardboard.
oh yeah, let me show you the materials.
Because like,
one sec.
Something the size of like an 8.5 by 11, like standard sheet of paper.
Yeah,
usually,
yeah.
I think.
I have a box of push pins around here too. Here we go. Like, what I have is this. Yeah, it's like an 8.5 by 11 piece of cardboard, side of a wine box. Oh, Sage, look at you. Tito's, all right. Okay, so I've got some push pins and I had to tie a loop of string. I'm gonna teach you what this is all about later, but this loop of string, I think it started off about 30 centimeters long. Yeah, there you go. You want it to be about 15 or so centimeters long on this direction. Okay. That's for later during lab, but I'm telling you about it now. Also, a ruler would be extremely helpful. All right, let's get into our lecture today. In our last lecture, we learned about the local sky and the celestial sphere, and we learned about coordinate systems. I'm not going to say that's the funnest topic in astronomy, but it's pretty darn useful. And it's kind of cool to understand how your sky rotates. If you think about it, the average Egyptian or Mesopotamian or ancient Roman pig farmer probably knew more about how the sky rotates than you do. And yesterday's class was an attempt to correct that problem. Unfortunately, the equatorial system and the horizon system are really confusing, especially when you try to blend the two together. And we saw a little example of that confusion today during our homework session, where we worked on the first 3 problems. The last 2 we're going to include in today's lecture. So if you missed that homework session, Kathy, you can at least get 2 of those questions, but you're going to have to go back and watch that video again, right? Okay.
Yeah.
But you already seem to have done that because you turned in your homework. I haven't really graded it yet, but we'll get to that. Okay. What's confusing about the 2 coordinate systems is they're used in different ways. Let's take a look at a picture from last week's TV show where we looked at this excellent diagram of star tracks or diurnal star circles, whatever they're called. It's the path that stars make as they rotate through the sky. When you stand on a field somewhere in your local sky, you tend to want to use the horizon system to describe the motions of stars because it's easy. And so if you're standing here where this green arrow is, you could talk about a star on this blue circle in terms of its altitude, its degrees above the horizon, and you could talk about its azimuth, which would be its degrees along the horizon. But if you follow this blue ring, as the star rises in your sky, its altitude and its azimuth are constantly changing. On the other hand, if you want to talk about the declination of the star, well, that's something that stays fixed. Each of these rings, the red ring, the blue ring, the purple ring, they have fixed declinations. Stars rise and set in your local sky, but their right ascensions and declinations are fixed to the celestial sphere. Let's see if you guys remember enough about declination that you could guess some reasonable numbers for me. We'll start off on the easy side. What would be a reasonable declination to guess for the red ring? What's the declination of that red ring? You may want to review the definition of declination in your notes if you can't remember.
Would that be 0? Because it's
Correct.
on,
Ian, how do you know that's 0, Ian?
because it's on the celestial equator?
Yeah, the definition of declination is degrees plus or minus from the celestial equator. So if you can see that the red ring is the celestial equator, then you know it's 0 degrees. Okay, someone besides Ian, because he's too good at this now. Give me a reasonable guess for the declination of the blue ring. I guess we can have Ian do it if none of the rest of you can, but how many degrees above the celestial equator would you say that blue ring is?
23.5.
Okay, that's a reasonable guess, Ryan Spaveled. But you know what, Ryan? I'd say if we forget about the ecliptic for a moment, I'm going to argue that this blue ring is about 1/3 up the celestial sphere. So I would have said positive 30 if you had asked me that question. But obviously, positive 23.5 is a totally effing reasonable guess. How about the purple ring?
$60.
Positive 60. Positive 60. How about the orange ring?
Negative 33.
Or negative 30? How about the yellow ring? Just anyone. Put me out of my misery, please.
Negative 60.
Negative 60. And then down here would be negative 90, okay? You can see that declinations superimpose onto the sky in a kind of awkward way. That's because you are halfway up the sphere from the equator to the North Pole, right? So declinations have a kind of awkward relationship. Last week, you practiced using declinations and right ascensions by guessing the RA and dec of the 4 cardinal points. Today, I want to burn a little class time practicing the horizon system. I think you guys are going to be good at this because you've already done today's homework, but it's such an important little lesson that I want us to do it. We're going to make a 2D drawing of the local sky. So get out your ruler, get ready to do some Bob Ross shit with me. Note to self, we got to get back to those. Okay, this title of your notes will be called a 2D view of the local sky. And this is for Rhode Island because we have to represent our home state here. We're going to do this very similar to how I did it in the first lecture. Leave yourself some headspace. Make a line on your page. If you've got a ruler, make it about 10 centimeters long or so. And then mark the midpoint of that line as carefully as you can. That's the center of the line. I'm going to use the radius of my line to mark several points along the dome. And that's going to help me make a nice, neat dome. Remember that trick? I'm basically kind of creating my own homemade compass here. I'm marking a bunch of points. For you guys, it will be about 5 centimeters. For me, it's about 30. And these points will just kind of help me make a snazzy looking dome that doesn't suck. Okay. And now I'll kind of connect the dots here. Oh, flubbed it right at the end. Sure enough, a pretty reasonable dome comes out if you do this, okay? Okay, let's put an observer in the center of the field. That's you. Let's make sure we label our directions. This is a north to south slice. We'll shade in the ground just a little bit, although this is not really supposed to be a 3D drawing. Let's draw in the observer's zenith as a reference point on the local sky. Draw a line to the head of your observer and mark it with a Z. Let us also put on the north celestial pole in this diagram. Hold on a second here. We already have an inkling that it should be about close to halfway up. Label that NCP for North Celestial Pole and put Polaris there. We basically did this last time, but we're doing it again. I think this is a good skill to have. It can help you solve problems, especially, you know, on a test. Nudge, nudge. And we'll draw in, we can't really draw in the full celestial equator because it runs east to west. But we know that the celestial equator should be at a 90-degree angle to Polaris. So we can draw the point where the celestial equator intersects with the meridian. Now, don't mind me. I'm going to be busting out my $10 vocabulary words. I hope you guys can follow me when I say fancy talk like that. This, my friends, is a two-dimensional view of your local sky, a cross-section sliced north to south. Your meridian is this arc here. This 2D drawing is really helpful to understand the geometrical relationships between different angles in your sky. Now, in honor of Greeks who loved geometry, I am going to label these 4 angles with the first 4 letters of the Greek alphabet. Alpha looks like a Jesus fish, okay? Beta looks like a little squiggly B. Gamma looks like a squiggly Y. And delta looks like a squiggly D. So alpha, beta, gamma, delta, the first 4 letters of the Greek alphabet. I hope you guys can read those. This marker is a little bit light. Let's do a little practice session together, shall we? One of these angles, alpha, beta, gamma, delta, represents directly your latitude on Earth. Which angle? Now, you guys are probably going to have a head start in this because we kind of did this in homework already, but I think it should be done in lecture. One of these angles is a direct representation of latitude based on the definition of latitude.
That would be beta, wouldn't it?
It would, Ryan. How did you know that beta would be your latitude?
Muted. Beta is the latitude because It's the angle between the celestial equator and the zenith.
Okay. I like where you're going with this.
It-
And
Uh,
let's draw under Earth underneath. The hard thing is to translate from your local sky to the kind of global Earth picture, right? You're standing, the observer is standing here. The North Pole should be at the same angle as the North Celestial Pole. So I'll try to make this parallel as best I can. Okay, so there's the North Pole. The equator should be parallel to the celestial equator. In fact, it should run in the same direction. So here's the equator. And you're standing somewhere up the globe. In Rhode Island, you're almost halfway, but not quite. Remember that your latitude and your longitude are angles. And the definition of latitude, well, I didn't do that great. The definition of latitude is it's the degrees of your feet north of Earth's equator, correct? So if latitude by definition are your degrees north of the equator, well, the equator points towards the celestial equator, and your head and feet point towards the zenith. So Ryan, you did good when you said to me, it's your latitude because it's the angle between the celestial equator and your zenith. What I wanted you to ... follow up with is, therefore, it is also the angle between the Earth's equator and your feet, and that is the definition of latitude. You see what I mean? Being able to translate between this picture and this picture is an art. But I hope by twisting the Earth sideways, you can see that relationship, okay? All right. We also know our latitude from last week's lecture. It's 42 degrees. So we'll plug that in. One of these angles, alpha, beta, gamma, delta, one of these angles represents the altitude of Polaris. Which of these angles represents the altitude of Polaris?
It would be delta is the fourth one, the one on the right.
Yeah, and Ian, can you just walk me through how you knew that?
I mean, seems pretty simple. It's just how far Polaris is above the horizon, right?
Yeah, it seems simple once you get it, Ian. Before that, it might not be so easy to Kathy, who didn't take my 1010 class, but that's okay. She'll learn eventually. So the angle here, delta, is the degrees of Polaris above the nearest horizon. The nearest horizon, of course, being this point, your northern horizon. So this is the altitude of Polaris. Feel free to ask any questions if you're confused on that point. Okay. Obviously, there is a 90-degree angle. I'm going through this argument slower. I went through it quickly during homework. The angle between the celestial equator and the north celestial pole is always a 90-degree angle. What does that make gamma? Like, how many degrees is gamma?
48. Oh, excuse me.
Because 48 degrees plus 42 degrees is 90. I spy another 90-degree angle between the zenith and the horizon. What does that make delta?
42.
40, yeah.
42 degrees. And for completeness, what is alpha?
48 degrees.
48 degrees. That's the altitude of the celestial equator. Okay. 48, 42, 48, 42. Now, we did this for a Rhode Island local sky. But think about it. It's always going to be a 90-degree angle between the equator and the North Pole. It's always going to be a right angle between the zenith and the horizon, no matter where you are on Earth. And the latitude will always be the angle between the celestial equator and the zenith. So even though these four numbers are particular to Rhode Island's local sky, in a way, we have proved a fundamental result that is true wherever you go on Earth. And it's a useful thing to remember, which is why we did this exercise. I'm going to erase down here, and we're going to write down the key takeaway from this little game that we just played. The altitude of Polaris is equal to your latitude. And that's a cute little trick that you can use to remember how to solve problems in astronomy. Put some stars next to that so that you remember this at some later date. That's kind of a big deal. This is the basis for celestial navigation. It's also the basis for trying to understand how your local sky changes if you go to different places on Earth. Guys, got that lovely drawing? You're going to want to keep that in your notes, okay? Promise that's useful. Let's practice it. This was kind of like some of our homework problems. I wish I had done this before the homework, but sometimes life sucks a little bit. I'm erasing. Shout at me if you have an issue with that, okay? Okay, so let's just try 3 quick examples. Or maybe 4. Here's a question. Describe the location of Polaris in the Rhode Island local sky. How do we do that?
As in, like, give the coordinates for it?
No, that would be question 2.
Oh, okay.
Question 2 would be, what are the global coordinates of Polaris? Let's try to answer both of those questions and distinguish between the two. It's about which coordinate system you should be using, Ian. If I want to describe the location of Polaris in my Rhode Island local sky, what coordinate system should I be using?
It's just called the horizon system, right?
Correct. So we're going to use the horizon system. And what 2 angles do we need for the horizon system? Jesus, guys, you scare me.
The altitude and azimuth.
Thanks. Okay, so give them to me then. Anyone. I don't care who knows it.
Well, the altitude we just said was 42 degrees.
Good. That was a test to see if you had a short-term memory longer than about 10 seconds. You've passed that test. All right. The altitude is equal to your latitude, 42 degrees. What about the azimuth? Azimuth is kind of like direction. So this is kind of like what color is an orange, or who's buried in Grant's tomb, or what's the direction of the North Star? Oh, I don't think you guys are with me today.
Is it north?
Oh, shit. Okay. What would be the technical azimuth of north?
0 degrees.
Good. All right. What are the global coordinates of Polaris? What system do you use for global coordinates?
Don't we use geographical?
No, geographical describes positions on Earth. We're looking for
Okay.
positions on the celestial sphere. It's kind of like geographical coordinates. It's the third system. It's the equatorial. Oh,
Yep.
wait, I want to hear from Katie. Katie's our new
Sorry.
friend. Katie's special because not only is she a new friend to the live show, but she hasn't taken the 1010 course like the two Ryans. And presumably she's not a math major like Sage. Now, being a math major doesn't necessarily help you, but it kind of does if you're good at math because you're used to doing geometry stuff. Kathy, what do you think?
The Equatorial System.
Booyah. Now, I'm going to warn you, this is a tricky question. Do you think you can give me either of the coordinates? Well, first of all, I know. Now I'm going to ask for more. See, you're going to regret volunteering. What are the two angles that we use in the equatorial system?
The right ascension, that one, right? And then the declination.
Good. Why don't you start with the declination? What would the declination of Polaris be? Assume it's sort of at the North Celestial Pole.
What's the degrees from the celestial
Correct.
equator, right?
It's the degrees from the celestial equator. Okay, you got a good memory. I like it. So here's Polaris up here. How many degrees from the celestial equator would that be?
90.
Positive 90,
Positive 90.
because it's above the celestial equator. Okay, so you've got the declination. What about the right ascension? Here we might want to use a
That's
more.
the hours
Keep going. The hours what?
with the definition. The hours measured eastward from the spring equator.
Yeah,
The equinox.
equinox, the spring equinox.
That's what.
But okay, yeah, what you said, sort of. Okay, look. So here's Polaris. Let's look at it from a different way. There's Polaris there. How many hours eastward or counterclockwise from the spring equinox is that?
18?
Let's phone a
Where am
friend.
I going from? Hold on.
Hold on, Kathy. Let's phone up Sage and see what Sage has to say about this.
I have no idea. It looks like it's in the middle.
Yeah, it kind of is in the middle. That's my point.
Oh,
Ryan's.
it's equidistant. Sorry.
Oh, wait, hold on. No, explain that better. Math man,
Oh.
explain that better.
Well, if it is in the middle, then it's the.
I don't like,
same
first
distance
of all,
as
I
the point.
hideously object to the term middle.
Center.
It's not really at the center of anything either, really. We have to precise up our language here.
If it's equidistant, though, it would
Equidistant from what?
the celestial equator.
Right. There is no point on the celestial equator that's closer to this, but also don't forget about what right ascensions are. They're like tangerine slices. That also
Yeah.
implies, Sage, that every tangerine slice must pass through the North Celestial Pole.
which
And
is-
therefore, if all of the tangerine slices are right ascension, all right
Yeah.
ascensions
Yeah.
pass through the North Celestial Pole. In other words, what can we say about Polaris? Polaris's right ascension, Sage?
So undefined.
It's undefined or degenerate,
Degenerate,
is how the
yeah.
math people likes to put it, okay? So the right ascension is undefined. I prefer the term degenerate. Another term is multi-valued. Every line of right ascension passes through it. Of course, you guys know the drill by now, right? I just lied to you because sometimes lies are better than the truth. And this is a case where if we had said the North Celestial Pole, that would have been perfectly true. Remember, however, that Polaris, hideously enough, is not quite at the North Celestial Pole. Let's find out what the actual RA and declination. Oh, wait, shit. I forgot there was a Jeep or something. Polaris star. Okay. Let's see what the actual coordinates are, because for some real-time show and tell, here's a little star map showing, can we zoom in on that bad boy? Showing that Polaris is just a smidgy lily widgy off the north celestial pole, right? And according here, they always have the RA and deck of stars like this. It's not actually positive 90, it's positive 89 degrees and 15 arc minutes. Holy cow, I thought it was half a degree off. It's actually 3/4 of a degree off. The right ascension is 2 hours and 31 minutes. And what that tells me is, well, how do I explain this to you guys without being more confusing? If it's off from the north celestial pole, if that's 0 hours, that's probably 2 right there. So Polaris is just off by 0.75 degrees in that direction. All right, whatever. The real purpose of those two questions was to highlight the differences between the horizon system and the equatorial system, and to figure out if you could use them in the appropriate context. Now that you've learned, let's try some more problems. This time we'll do it orally because I don't feel like writing it all down. Describe the altitude and azimuth of Polaris from the north celestial pole. Sorry, well, you're not in the sky, you're on Earth. Describe the altitude and azimuth of Polaris if you're standing on the north pole of Earth. So here you are, you're standing right there. Altitude and azimuth of Polaris. Can you do it? Anyone at all? And I thought we was cool, but I was wrong, wasn't I? Maybe some visual help. Maybe you all need some. Honestly, all you need to use is the thing that I put the stars next to with all the fire beams. It's the altitude and azimuth of Polaris if you're standing on the north celestial pole. I bet you can't visualize that. Let me help you. What did we learn about the altitude of Polaris? Okay, now I know that I have to write this down because I'm going too fast for you. I thought I was just the right speed, but now I realize I'm too fast, okay? So let's try this again. So question 3. Describe the location of Polaris at the North Pole of Earth. You should be able to give me this one right away because you learned an important rule about altitudes of Polaris, didn't you? Someone read it off the page for me.
It's equal to your latitude.
So what's the latitude of the North Pole?
Oh, that's where I was stumped.
You're kidding me.
0 or 180? 90? Sorry, I'm really bad at direction.
Latitude is like a ladder, right?
Yep. So 180.
There's no such thing as a latitude of 180. That doesn't exist.
Gotcha.
Latitudes are 0 at the equator. They go up to 90 degrees north and down to 90 degrees south.
So 90 north.
All right, that's your latitude. So what is the altitude of Polaris from the North Pole?
90 degrees north.
90, no north, just 90 degrees. Altitude is just a number, all right? And you can see that in my drawing here. Altitude is your degrees above the horizon. If you're standing on the North Pole, it doesn't really matter which direction. Oh, is this? Yeah, North Pole, right? Polaris is up here. It's directly over your head, 90 degrees altitude. It's also your latitude, 90 degrees north. What is the azimuth of Polaris? Why do they have, oh, it's all south because they're at the North Pole, right? So what is the azimuth of Polaris from the North Pole? Here's
Would
something
it be
weird.
undefined?
Very good. Now you're catching on. You know, if you're standing at the North Pole, there's no north, south, east, and west anymore. It's only south in every direction. Isn't that fucked up? That's weird to think about, right? North, south, east, and west break down at the North Pole because any direction you go is south. That's cool. And that's right. It has no azimuth. I guess I could go on, but I won't. Learning how to do this stuff can be kind of tricky. That's why we're asking these. I'm asking these problems to get your noodle cooking and to have you practice it, okay? I wanted to do a question to describe the path of the celestial equator in your local sky, but you'll remember that we did that in homework for question 42C or 43C. I can't remember which one it was. So review that in your homework. Okay, we got to change topics a little bit. I'm going to leave celestial coordinates behind. I'm sure everyone will be grateful for that. I want to talk to you guys about planets and orbits. Let's have a think about the sun and the moon and what they're doing, and then we'll move on to planets. So I'm going to show you a kind of cute slide from my 1010 class. They've got there's a slide here that I like a little bit more. It's kind of better graphic design, even though it doesn't have north on the right-hand side. So I kind of dig this picture here. This shows you the path of the sun on 3 different days of the year in a random arbitrary local sky that's probably similar to Rhode Island's. Notice that on the day of the spring equinox, the sun will travel the celestial equator. So this is the question that I was actually just referring to. Can you guys like verbally describe to me the trajectory of the sun on the spring equinox? So it starts here, goes up to there, and then it sets down there, right? So what's the altitude and azimuth of this point? Or give me the altitude and direction.
0 and east, which is 90.
Sure. So it starts off 0 degrees east. It goes up to a maximum altitude of oh, snap. Oh, snap. Okay, never mind. We are writing this down. Let's try this. Question 4. Describe the path of the celestial equator in the Rhode Island local sky. Rise, reach, and set. Sage gave us 0 degrees east for the rise. What about the reach? That's the highest point. Maybe we should look at it using a slightly cruder diagram. Ooh, nah. In this diagram, I like it better because it has north on the right-hand side. It's not as fancy as the previous diagram, but north is on the right-hand side, so it reminds us of the drawings that we made.
So 42. So
Look at your alpha, beta, gamma, delta, gamma again.
48.
Yeah. From the south, this corresponds to the angle alpha that we just discussed, right? That angle is, ooh, you're getting a fax from Darth Vader. Okay, so.
That's why I was like, before when it rang, I like jumped. It was terrible.
Okay. So there we go. That's 48 degrees. That's the alpha angle that we just did, right?
Gotcha.
What's the direction?
That's pointed south, so that's going to be 180 degrees.
We'll just put south for now. I want to drill into your head that azimuth is the same as direction, so that's what I'm doing. And what about the set point?
0 west.
And this is also equal to the path of the sun on the spring and fall equinox. On the spring and fall equinox, the sun is pegged to the celestial equator. What the hell is this? This is the third time I got a call. Just hold on a second. Okay. Sorry about the interruption there. Okay. The moon is a little bit more complicated than the sun. The moon's orbit is inclined with respect to the sun by about 5 degrees. So even though the moon's path is more complicated, because it depends upon the time of year and whether the moon is above or below the ecliptic plane, the way I think about it is, since 5 degrees isn't too much wiggle room from the ecliptic, the moon kind of follows a similar path to the sun. Basically, the sun is always going to rise in the east and set in the west, and it's always going to move through your southern sky within about 20 degrees of the celestial equator. The moon is kind of doing the same thing. It's kind of in this area, rising in the east, setting in the west, and it kind of warbles around between various latitudes in your south. But the moon's path is a little less predictable than the sun, but more predictable than planets. Planets are a little bit screwier. And do you guys know why? What's the deal? How many planets can you see with the naked eye?
Five.
Right. Can you remind us what they are, Ryan?
Yes, Mercury, Venus, Mars, Jupiter, and Saturn.
Very good. Now, I love telling students this who've never heard this little tidbit before. That means there are 7 astronomical objects that are not stars. There is 1 sun, 1 moon, 5 planets, and guess what? There's also 7 days of the week. Coincidence? I think not. That's because the sun is for Sunday and the moon's for Moon Day, and Mars got associated with the Viking god Zutog, and that became Tuesdag in Old English, and then it became Tuesday. Wednesday is literally the same as Woden's Day. The Vikings associated their god Woden with the wandering god Mercury, although the Viking god Woden is way cooler because he's a trickster and he shows up and, you know, diddles ladies and all this other stuff. He's a funny, Woden does some crazy stuff. Mercury, I don't know, he was a messenger god. In any case, Woden's Day became Wednesday. Jupiter literally turned into Thor's Day as Vikings and Romans clashed and mingled their cultures together. Their gods got all sort of mixed up. And so, and English, if you think about it, is a mixture of Germanic languages and Latin languages. So Jupiter became Thor's Day. Venus was associated with Freitag, and that became Friday. And Saturn is still kind of Saturn Day. So why am I telling you this? You may not realize it, but every aspect of timekeeping every aspect of calendars, from the days in a month, the fact that we use months, the fact that we use years and days at all, it's all connected to astronomical objects. Why? Because in the golden olden times, before there were Apple Watches and Nintendos and things, people used the sky as their clock, as their calendar. The sky was their clock and calendar. Now, we don't have time to get into that too much. I have a wonderful lesson on time, a painful, not fun lesson that I do in Astronomy 1010 on timekeeping and stuff like that. I'm giving that lecture tomorrow. For you guys, I'm letting you guys skip over that stuff because we're trying to like escape the solar system and get into some weird, wacky stuff in space. But we do need a couple of basic things from chapter S1. And we need a couple of basic things from chapter 3 on the history of astronomy. We have to learn about the orbits of planets. And to take you back historically to what it was like when you'd watch planets rotate around the sky, we know planets are not stars historically because, first of all, they're brighter than stars. And second of all, they wander or they drift with respect to the background constellations. So maybe we can start these notes in a cute way that's kind of useful, potentially, if you're interested in astronomy. Let's start with the following thing. How can I tell a planet from a star? There's a couple of different things. The first thing is they are brighter. And therefore, when you look out at night, the very brightest objects that you see in the sky that look like super insanely bright stars, most of the time, they're one of the planets. Now, there are times when none of the planets are up in your local sky, just from randomness. And then the brightest star in your sky might be Sirius if it's wintertime, or it might be Arcturus if it's summertime. But usually when you see a planet in comparison to stars, you can tell that they're just a lot more intense. The second rule that amateur astronomers use is this. Stars twinkle, planets don't. Does anyone remember why that is? I mentioned it in a previous lecture, but you know. Why do stars twinkle and not planets?
Isn't it because the planets planets are observed in arc minutes compared to stars where they'll be observed in arc seconds?
I'm impressed, Ryan Spavel. That is exactly right. Now, remember, both planets and stars are unresolved to your naked eye. But as you pointed out, even though they're unresolved, the angular sizes of planets are so much larger than the angular sizes of stars. I mean, remember this slide that I showed you? Jupiter is about an arc minute, whereas Betelgeuse is 0.05 arc seconds. So even though they're unresolved, the beam of light from a planet is much wider than the beam of light from a star. And the twinkling comes from air molecules kind of pushing them around. Even if these two things were true, that wouldn't be enough for ancient observers of the sky to realize that planets were not the same as stars. It's the third thing that really tips you off, and that's planets wander against the background sky or against the background stars. And this is why Greek astronomers, for instance, knew that planets could not be of the same class of things as stars. In fact, the Greek word where we get planet from, planetos, I don't know how to spell it in Greek. It's got all these funny letters. But planetos in Greek means the wanderer. You might be wondering, what does wanderer really mean? Well, let me give you a little cartoon depiction of that. Sometimes if you go out at night in the summertime, I think once I went down, what's that bar there along the bay that everyone loves, the Ocean Mist. I don't usually leave Providence because I'm like a worse version of Rhode Islanders that don't go anywhere. But one day someone tricked me into going down to the Ocean Mist, and I needed to sober up before I drove home. So I kind of went through this little hole in the fence and I sat on the beach there, and I looked up at the nighttime sky and I was shocked to see the constellation Sagittarius. Now, I normally don't get to see Sagittarius from the observatory in Warwick because there's trees in the southern direction and Sagittarius is kind of low. But if you ever get down to the coast at night and you're looking south, you can find Sagittarius by a grouping of stars inside Sagittarius called the Teapot. And I got all excited because I recognized it basically from this lecture in this little cartoon picture. And I went, holy cow, it really does look like a teapot. And so you can see the teapot this summer if you look for it. That's part of the constellation Sagittarius. Now, I'm sure if I could recognize the teapot while sitting drunk on a beach, so could some ancient pig farmers sitting around drunk on their logs or whatever they were doing, right? And so one day what happens is you go out at night and you see Mars, or rather you see this really big intense red dot, and it's way brighter than any other star. So you're like, huh, that's kind of special. And you see it kind of above the teapot of Sagittarius. And you think, well, nothing special there. It's rising and setting along with the teapot, just like the rest of the stars. What's weird is the next night when you're sitting on your log, you look up and you see, huh, I could have sworn that red star-like thing was like above the teapot yesterday. It almost looks like it's moved, but it could be that I drank too much grog or mead or something like that. And then by the third or fourth night, when you watch the thing, you say, okay, no, wait a minute, that's not the hooch talking there. That thing is actually shifting its position. Now, why would you find that weird? Because none of the other stars do that. And there's thousands of stars you can see. The relationship between this star and this star and this star, they never change. The teapot's always the same. You don't see the lid go drifting off over here, right? But here's this one really big bright thing that looks like a star, but night after night, it's drifting eastward along the ecliptic. Now, at first your noodle starts cooking. You start thinking, man, I know about some other things that drift eastward along the ecliptic, the sun and the moon. So maybe these things are as powerful as the sun and the moon. They're like my energy gods, right? Okay, well, here's what's really going to mess you up. And this is what bothered Greek astronomers a lot. They would watch these planets, these wanderers, night after night drifting eastward along the ecliptic. And then at key times of the year, they would wig out. Night after night, they would slow down in their motion. They would stop moving eastward. And then for a period of a week or two, they would suddenly start moving westward. Now, that would really screw your shit up because nothing drifts westward in the sky over the year. Everything's kind of going counterclockwise. So the fact that the planets would kind of change their minds and start drifting westward, and then they change their minds again, and then they start drifting in the eastward direction again. This little loop is what is known as retrograde motion, okay? It's a temporary westward drift along the ecliptic that planets make. I think that's worth taking a little note on. That's kind of like a classic astronomy thing. So planets undergo, here we go, retrograde motion. And if I had to sum it up kind of quickly and efficiently, I would say it's the temporary westward drift along the ecliptic made by planets. Of course, they do other wanderings as well. They drift eastward, but retrograde motion was kind of the special thing. Now, SAGE has plans to study mathematics. SAGE, think about this. From the Greek perspective, these objects in the sky, They weren't just some abstract twinkling lights. These were their gods. Like, this is a pre-Christian society, right? God wasn't some invisible old man in the sky with a beard who gets mad at you when you say cuss words or something like that. Their God was not some abstract invisible deity. Like, if you wanted to see where the gods were, they were right there. There's Mars. Oh, and by the way, there's Jupiter. You could just look at your gods and you could see them on your sky. Not only could you see your gods, but the gods seemed to be crazy and occasionally would change their minds about where they were going and would kind of go back the other, and then they would change their direction again. Perhaps this even led to a sort of Grecian irreverence towards the gods, where they, you know, they didn't have tons of respect for them. They were almost like nemesis more than anything else. Well, the desire to understand the insanity of the gods is what gave us mathematics. We actually developed so much of mathematics just trying to explain these retrograde loops in the sky. For instance, Plato believed that the orbits of planets had to be perfectly circular because circles were like a heavenly geometrical form. And so what did Greek geometricians start doing? They came up with kooky ways to explain retrograde motion. Now, I don't have time to get into the whole story, although it's quite interesting. But some of the early attempts, as the two Ryans know, they took my solar system class, which gets into this a bit. But one of my favorites was the use of epicycles. So they believed that since Earth was the center of the cosmos, that's the Greek idea, that the reason why planets did retrograde motion is because they were orbiting on secondary circles that orbited on top of a primary circle. So they invented this kind of retrograde motion. Sorry, they invented epicycles. This is called an epicycle. They invented these epicycles to explain retrograde motion. I'm not going to test you on that, so don't bother writing it down. Okay, obviously that was wrong. We needed to learn some things about astronomy before we could figure out what was going on there. The first thing that happened that set us in the right direction was Copernicus, a famous Polish cleric in the 1500s or so. Nicholas Copernicus, a Polish cleric, came up with a new model of the solar system. He tried to improve upon the Greek model by placing the sun at the center of the solar system. And this, of course, was a controversial thing to do. But one of the strong arguments that he had in his favor is that if Earth orbited the sun, he could explain retrograde motion in an elegant way, which did not involve epicycles or saying that the gods were crazy. And his idea was that, and this is the true reason why we have retrograde motion. It's kind of a geometrical effect when Earth passes by planets. So for instance, check this out. In configuration 1, in configuration 2, and in configuration 3, both Earth and Mars are orbiting eastward or counterclockwise along the ecliptic. As Earth catches up to Mars, it's seeing Mars kind of shifting in this direction, which is eastward on the sky. However, as Earth passes by Mars, configuration 4, 5, and 6, it kind of gets ahead of Mars in orbit, and it makes Mars appear like it's drifting backwards against the stars. Essentially, this is an effect of geometry called parallax. If you hold your thumb out stretched at arm's length and you blink your eyeballs back and forth, you can see your thumb kind of shift back and forth against the background. And it's just an optical illusion caused by the fact that you're basically drifting past Mars in orbit. Of course, after the retrograde motion happens, which might be for a few weeks, as Earth and Mars continue moving forward in orbit, it appears like Mars is now drifting eastward again. And you can see these kind of effects even when you drive past a person on the highway. It kind of looks like they're traveling backwards with respect to you. Or there's all kinds of funky geometrical effects like this that happen. So the proper description of retrograde motion turns out to be that Earth is passing by orbits. And by the way, it does this for interior planets like Mercury and Venus, as well as Mars, Jupiter, and Saturn. That's why all the ding dongs on your social media thing are telling you that Mercury's in retrograde right now, and they're all, you know, your computer's going to switch off or whatever the shit they talk about. So obviously they don't know what they're talking about, but now you do know what they're talking about, even though they don't know what they're talking about. They're talking about retrograde motion, and it's basically an illusion, and it doesn't matter. One of the problems that Copernicus had in convincing people that Earth went around the sun is that he was kind of philosophically biased towards perfectly circular orbits, because 1,000 years or more before he had, actually 1,500 years or so, sorry, 2,000 years before Copernicus had thought to do this, Plato told a bunch of his students that the orbits of planets should be perfect circles, and that idea persisted like a virus throughout intellectual circles from Hellenistic Greece all the way up to Nicholas Copernicus. He could not imagine that orbits could be anything but circles because Plato told me so, and they didn't know any better. Unfortunately, his model wasn't very good at predicting the positions of planets, and for that reason, it was easy for Jesuits to persecute him as a heretic, because they said, well, first of all, you're saying Earth isn't very important. It's not in the center of the solar system. And check out your bullshit model anyways. It can't even describe the position of Mars or when it's going to go into retrograde motion. And that muddles the damned argument, right? After Copernicus, people who got intoxicated with Copernicus's idea, they attempted to make the heliocentric solar system work. And eventually the person who figured it out was this German astronomer, mathematician named Johannes Kepler. He had a tutelage under this famous Danish astronomer, and when the Danish astronomer died, he stole all of his data for the orbits of Mars and fled to the forests of Germany to try to make the Copernican solar system work, because he was philosophically biased towards it. All of the history of science is muddled with stuff like this, which is really cool, actually. And in fact, this brings us around to our big topic of the day and what we're going to do in our lab. Johannes Kepler solved the problem of planetary orbits pretty much forever. He came up with something so incredibly useful that we still need to study it in our most basic astronomy classes today. He discovered that the orbits of planets were not perfect circles, but were part of a geometrical class of objects called ellipses. For now, our definition of an ellipse is going to be a squishy circle, okay? But today you're going to learn how to make a proper ellipse. What you're going to do is you're going to put 2 thumbtacks into a piece of paper. You will tie a loop of string around those 2 thumbtacks, and you will hold the string taut with your pencil. And as you drag it around the paper, a perfect geometrical shape will come out called an ellipse. It's an oval, but it's a particular type of oval. Now, for those, since we have a couple of math fans in the audience, or at least one, let's talk about the real definition of an ellipse. The real definition of an ellipse is that the perimeter of this triangle must stay fixed. That's why we hold the string tight. So if the perimeter of this triangle stays fixed, the geometrical shape that comes out is called an ellipse. I would show you the equation of an ellipse. I would do this if it weren't for the fact that it would probably scare you, or at least scare some of you. So the equation for an ellipse is maybe a little bit over our pay grade here. Whoa, which one do I want here? Yeah, we don't want to be looking at stuff like this. I mean, we do, some of us do, but not everyone. Honestly, it's about the level of an Algebra 2 class, but not everyone's had that, so I won't go nuts on you here. We don't need to understand the equation of ellipse to understand how ellipses work. We can start by drawing a cartoon shape of them. By the way, I'd like to just kind of go off on a tangent for a second here, another tangent, actually. Sorry, I'm really scatterbrained today. Ellipses are part of a class of geometrical objects called conic sections. And there's a thing here. How many ways can you slice a cone? It turns out there's only 4 ways to slice a cone. If you slice it horizontally, you get a shape called a circle. Slice it through the side, a shape called an ellipse. Slice it through the bottom at a random angle and you get a parabola. If you slice it perfectly vertically, you get another shape that looks like a parabola, but isn't a parabola. It's called a hyperbola. Now, circles, ellipses, parabolas, and hyperbolas are a class of objects in mathematics called conic sections. Johannes Kepler was kind of interested in conic sections. They were like a curiosity for him. Over time, he realized the first part of the issue. He realized that ellipses were the proper geometrical shape of planetary orbits. What he probably didn't realize that he had stumbled upon a much bigger thing. All of the geometrical shapes of gravitational orbits and interactions are conic sections. I'm going to come back to that at a later time when you have a more sophisticated understanding of gravity. For now, let's make a crappy little ellipse, just like we're going to do in lab. I want this one to be in your notes so you can study from it. Okay, so an ellipse for now is going to be a squishy circle. Let's start by making a line on our page. Once again, you might want to use 10 centimeters as a reference. Make a 10 centimeter line and then mark the midpoint with a dot. Now I want you to make another line, but I want this one to be shorter than the first one. I'm going to make mine a little less than half. Nope, I'm going to make it half. I lied. Wait, what? No, actually, it's a little less than half. Sorry. Okay. So I've made a long line connected to a short line. Now, since we're cheating, this isn't a real ellipse. And by the way, Ian, who is still in the background, you know, when you drew your ellipse, you could have used this trick to make a better ellipse than the one you drew. This isn't the right way to do it, but it's kind of an effective cheat. Okay, an ellipse is parameterized by two focus points. And the focus points are where we would put the thumbtacks. Now, I could try to calculate my focus points, but I'm not going to do that. That's going to bore the crap out of you guys. Let's just wing it and make it up. This is a fake ellipse. So let's just make, one thing I will do is make sure that my focus points are equidistant from the center. That's something I can do. Okay. This is focus point F1, focus point F2. Now let's label some parts of our ellipse together, shall we? This axis is called the major axis. We're going to do this again in lab, so I'm doing it quickly. This is the minor axis. Couple of parameters of interest. The distance from the center of the ellipse to one of the focus points, I call it X. X is your focus offset. Another important property of our ellipse is the distance from the center to the edge of the ellipse. That gets a very special letter in astronomy, A. A is the semi-major axis of the ellipse. There is a third parameter of interest. That parameter is called E. E can be calculated as X divided by A. It's the ratio of the focus distance to the semi-major axis. This quantity is called the eccentricity. And basically what the eccentricity means is it's the percent squishiness of your ellipse. Where the domain of E is greater than or equal to 0, but less than 1 always. Take that down and then we'll explain it. Looks like you guys have it. All right, let me show you some cartoons here. Oh, son of my eye. Let me show you eccentricity. I think there's a little cartoon picture that shows a number of different, yeah, this isn't great, but it'll do. Shit. I hate how they give you the crappy small one, not the big one. Oh, control minus, 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 minus. Okay. Here we go. Notice that an eccentricity of 0 is a perfect circle. That's 0% squishy. As the focus point gets further and further away from the center, your eccentricity can go to 20%. Somewhere around 50%, it gets egg-shaped. Around 80% or 90%, it gets very oval. And if you get up to 95 or 99%, it starts to look like a cigar. Notice that even 20% eccentricity is still pretty circular-like. You have to get up to 50% before you even notice it at all. On the other hand, what about the eccentricities of the planets? Eccentricities of the planets. They have a data table on this in your book here, but let's take a peek. The orbital eccentricity of Mercury is 21%. The orbital eccentricity of Venus is 0.7%. Earth is 2%. Mars is 9%. Jupiter is 5%. Saturn is 6%. 5%. 0.09%. Pluto is a little bit extreme at 25%. What would you say if you had to draw away a big conclusion about the orbital eccentricities of the planets? This is, part of science is looking at a bunch of numbers and trying to make some kind of crazy sense out of it all. What do you guys think? What would you say about the eccentricities of the planets?
They're very circular.
They're wicked circular, right? In fact, they're so circular that you could really forgive some of those ancient Greeks like Plato for thinking the orbits of the planets were perfect circles, because they really were damned close to it. You had to have very careful observations to find the differences. In fact, famously, Johannes Kepler, when he discovered that the planets were ellipses, he did so through a very careful study of the orbital data of Mars. Now, randomness made Mars's eccentricity 9%. If we had lived in a solar system in which Mars was also really close to like 2% or 1%, I don't know if Kepler would have had enough observational precision to discriminate that. And we might not have figured out that planets orbit on ellipses, and that would have screwed up a whole bunch of other scientific discoveries. Shit, if Mars's orbit had been more circular, you and I could still be roasting weenies on the campfire and driving our horse and buggy to church, okay? So it's not the same world because of this. Now, if you were a pesky student, and I do enjoy an occasional pesky student, you might ask me a question, why would the orbits of planets all be so circular? There's an answer to that. It's got something to do with the way the solar system forms, the conservation of angular momentum, and the fact that when little rocks are swirling around the sun and beating the shit out of each other, they tend to circularize their orbits through collisions. That's a bigger story, maybe for a different class or something. But planets, when they form into a solar system, they tend to bash each other's orbits into circles. Okay, with that being said, you know a little bit about ellipses. Now let's talk about a thing. There is a thing called Kepler's laws of planetary motion. He published them in a famous book called Harmonious Mundi, on the harmony of the spheres. And he had been sitting in the forest studying the orbit of Mars, and he discovered these three truths about planetary orbits. They are so good, even though they're a lie, even though they turned out to be kind of wrong. They're so close to the truth that they're a better lie to start with than anything else. And astronomers still refer to Keplerian orbits. It turns out that these shapes not only describe the orbits of planets, they describe the orbit of stars around the galaxy. Even galaxies that collide with each other are subject to Keplerian orbits. Kind of a big deal, kind of a thing you need to learn about if you're going to study Astronomy 101. So let's do that now. Kepler's three laws of planetary motion. After that, we'll take a little tea break, okay? So this is called Kepler's three laws of planetary motion. One of the reasons that I did not do those last two homework problems is they are based on this. So after tea break, if Sage or Ryan's could remind me to make sure we do the homework when tea break ends, okay? Okay, the first law of planetary motion is called the law of ellipses. It states the following fact. A planet orbits the sun on an ellipse, so that's part of it, but the other part is with the sun located at a focus point. That's sort of a big deal. The sun is not actually at the center of the ellipse, it's off from the center at the focus point. It might have been very tempting for Kepler to put the sun at the center, as Copernicus had, but he was too clever for that, all right? So as I describe these laws, just, take a peek. This is what we're saying, right? The planet's orbit is an ellipse. The sun is over here at the focus point. The second law tells us how the planet travels around the sun with time. It's not uniform motion, but the planet speeds up closer to perihelion and it slows down farther from the sun at aphelion. And this is known as the law of equal areas. The law of equal areas states a planet, by the way, sometimes people just shorten this to the law of areas, okay? A planet sweeps out equal units of area in equal intervals of time. So in order for him to model this, you might be wondering, what do you mean by equal units of area? He actually drew a line that connected the planet and the sun, and he would measure the distance it traveled in, say, 2 months. And then he kind of gridded out the area that it swept out into a bunch of little tiny boxes, and he'd count them up. And he found that by the magic of weirdness and math, that when the planet spent 2 months going from there to there, if he counted up all of those little boxes, that later on the planet would go from there to there in 2 months. That's clearly not the same length of distance, but that if he added up the area of the boxes in this little triangle, it was magically equal to the area of the boxes in that triangle. Now there's a thing going on there that I'll talk to you about later, but he didn't know what the thing was. He just knew that it worked. His third law, which is called the harmonic law, is a math equation. It's a very useful math equation that you guys are going to need to use all the time on your test. It says p squared is equal to a cubed, kind of a classic formula, where p is the period of the planet in units of years, and a is the average distance to the planet from the sun, of course, in astronomical units. Actually, that might not be obvious to you guys. Average distance to the planet from the sun. In astronomical units. I should mention there are two crummy little formulas that are not part of Kepler's laws, but are sometimes associated with them. And that's because they're kind of equations related to ellipses. You're going to see me use these equations today. You can calculate the perihelion distance of a planet by doing a times 1 minus the eccentricity. And you can calculate the aphelion distance by doing a times 1 plus the eccentricity. These were not originally a part of Kepler's laws, but they are part of the equations of an ellipse. I'm just going to introduce them now. Let's just jam them somewhere into your notes if you can. I'll erase up here. So perihelion and aphelion distances, very simple formulas. The perihelion, which I'll abbreviate peri, is a times 1 minus e. The aphelion, which I'll abbreviate APH, is a times 1 plus e in parentheses. You'll have to forgive me for going quick, but I was trying to get this in before tea break. These formulas and this formula are actually wicked simple to execute, but I'm going to have to train you on that. I'll do it after tea break, and we'll do a couple of homework problems, okay? So here's how this is going to work. It's tea break time. Kathy, if you watched the videos before, you kind of understand what's going on, right? Okay, cool. And you like tea break time too, right? Okay, everyone likes tea break time. So it's 1:46 iPhone time. I'm going to plug in 25 minutes because I brought back bagels from New York and I really want to get some cream cheese and eat one of those things. Okay, so 25 minutes so I can eat a New York bagel. That's a damn reasonable price to ask for, okay? And then when we come back, we'll do homework. We'll squeeze out a teeny bit more lecture and we'll do that lab wicked fast, okay? I'll see you guys in 25. Peace. Okay, welcome back, Astronomy 1020. Just before tea break, you learned about Kepler's laws of planetary motion. I'd like to remind the class that during today's homework session, homework number 2 is kind of wild and intense. There was a lot of difficult questions. And we didn't get to the last 2 problems, but I kind of almost did that intentionally. I thought it would be better to tackle those 2 problems now after Kepler's 3 laws of planetary motion. So I'm going to make a note to self. I don't have the, it's around 2:12 p.m. I'm not sure how that's going to tie into the recording, but I'll be able to find it. So let's take a look. Kathy, Ryan, and Ryan. Kathy, since you're starting this homework after the first 3 problems, that's fine. You can do them out of order. But what I think you should do if you're taking notes in a notebook is you should have a separate page where you do these 2 problems and then save a lot of space, like maybe 2 pages or something, or a front and the back of a page for the other 3 problems in this homework. Because I'm thinking that later on when you go to submit this or when you study, if half of your homework 2 is in one spot and half is in the other, you'll have a hard time finding them and keeping them together. Do you understand what I'm saying?
Yeah.
Okay, so be smart about how you plan this out, okay? Because I think that not only will it be nice to be able to take pictures and submit this work, it's also good when you're studying, or say at the end of the semester, if I'm like, hey, did you turn in homework 2 or not? You can say, oh, here's my homework 2, and all 5 problems will be together. You know what I mean?
Yeah.
Things like that are important. By the way, I did manage to check out, I started grading the homeworks, but I sort of ran out of time. I did want to take a look at the assignments that those of you who are here turned in, so I can tell you especially how the homework looks. Now, Ryan and Ryan have experience with me, so I suspect they will have pleased me, but let's just see. Here's Eva, or Evelina. I don't know how
I know I didn't please you. I can tell you ahead of time.
This is good.
Oh, wait, that's not mine.
Oh, that's Ryan's. Ryan, this is cool. You did exactly what I wanted. I noticed that some people in my, I graded the 10-10 homeworks last night by accident. This is good because it, oh, okay. Okay, he's got all the stuff I want. There's no rhyme or reason to how the pages are organized. So thank you, Ryan, but,
Yeah, the files wound up out of order or in reverse order.
Try. Oh, that reverse order is okay as long as there's some kind of logic to it. Okay, this is fine. I need to see that drawing though. Oh, hey, Ryan, we got beef. Listen now. I may not be the sharpest crayon in the 64 pack, but I know a 25 centimeter line when I see one, and that is not 25 centimeters. I am going to have a beef with that. How do I know that? Because I know 25 centimeters should go across an entire page. You know what I'm saying? Like, I actually wanted your drawing to scale. And if you didn't have a 25 centimeter ruler, you needed to fake it successfully enough. So I'm going to take issue with that, but that's just a point. But remember, when these things say, I want you to draw this to scale, that means do it. Okay?
You got it.
Here's Sage. See, now Sage did it right, Ryan. That's what a 25 centimeter line should look like. So that I am pleased with. In any case, so far I like all the stuff I'm seeing here. I'm really worried about people who didn't get the memo about typing. If you're going to try to type this up, you need to do a really, really fantastic job. And you probably aren't going to be capable of doing that. So you probably shouldn't type it up. All right, this is good. I want to cover this before we go on. Kathy, that looks great. I can already tell that's going to be just what I want. Okay, so everyone here basically did what I want, except for Ryan, who did what I want, except he didn't make the damn thing to scale. All right, so you'll never do that again, Ryan, correct?
Yeah.
All right, good. Buy a ruler. All right. So we've got this stuff down here. Let's try to hit that those final 2 problems, shall we? Kathy, we haven't heard from your lovely reading voice yet, so if you know the drill from watching the video, call up those questions from the homework session from chapter 3, and remind me the problems are 49 and 50, I think. Oh, sorry, 53 and 54. So open up chapter 3.
Give me 1 second.
Yep. So right click and open up chapter 3 PDF. And we're going to do 53 and 54.
Just make sure I got the right ones. You said chapter 3?
Yeah.
Okay.
Yes, please. So this is
50.
homework number 2, continued.
All right. A newly discovered planet orbits a distant star with the same mass as the sun at an average distance of 112 million kilometers. Its orbital eccentricity is 0.3. Find the planet's orbital period and its nearest and farthest orbital distances from its star.
112 million. How many zeros are in a million, Kathy?
6, right?
So the distance is 112 million kilometers. What other givens did they provide for us?
Its orbital eccentricity is 0.3.
Okay. They also mentioned it's one solar mass, or the same as the sun. And then was there an A and a B, or did they just mush it all together?
They just mushed it all together.
But they asked for like several things, right?
Oh yeah, find the planet's orbital period and its nearest and farthest orbital distances from its star.
Okay, and we know what those vocabulary terms, nearest and farthest distances, are called. I'm sort of forgetting the names of those things here. What do we call that when it's close to the sun and far from the sun?
Hold on. Down. It's the perihelion and the aphelion.
Very good. That was good enough for me. Perihelion and aphelion. Okay, so I'm not just picking on Kathy. I'm talking to all of you guys. Let's tackle the period first. What formula are we going to use to do that?
P squared equals A cubed.
Exactly. But we got a little problem here, Ryan. What's the problem?
Do we have to reverse it?
It's not that we have to reverse it. We could probably solve for period. Maybe I'll do that in just a moment, but it's not about reversing it. It's about the formula itself. Every formula is like a little monster. You got to feed the little monster what it wants to eat. You can't feed your cat dog food. I mean, you can, but it's probably not a good idea. You don't feed your dog cat food, although you could, but it doesn't work so well. What's the damn point that I'm trying to make? Oh, Evelina typed hers. Evelina, we need to take a look. Evelina, it's not about whether typing, it's how you typed it. I thought I had checked yours. I just saw Evelina's comment. Where is she? I want to grade her.
Horrible.
Am I going to be mad at you, Evelina?
Yes, you are.
All right, yeah, I'm fucking furious at you. Okay, listen, Evelina, I'm glad you're here with us now, but buddy, this is not going to cut it for me. Okay.
Yeah.
Now, Evelina, I'm going to pick on you a little bit, but I'm doing this for a reason. I'm hoping that all the other people who didn't watch my videos will suddenly now be watching like you are and will learn something from this. I am also a monster, and you got to feed me what I want to eat. All right. And I want to see dimensional analysis. I also want to see complete answers to all the parts of the questions. I also need you to use an equation editor. You cannot give me this stuff because from my perspective, this kind of stuff is unreadable. I can't follow your math. Now, I said this before, but I've discovered that saying things a few times, like maybe even 10, is a good idea. When you do if you are going to attempt to type math, you can only do that if you are skilled enough to use an equation editor. And I tried to give people a few hints on how that's done.
Oh no, I'm just gonna go to handwriting. I'm gonna just do
yeah,
because I'm not an expert on that. I don't know how to work that, so I'm gonna just stick to handwriting.
It's not that it takes you don't have to be a rocket scientist. You just go and you type in equation, and then you type in 25 centimeters, and then you do a proper multiplication bar, and then you do a division bar. There's all kinds of ways to do this.
Oh, okay, I see what you're saying.
But you're kilometers on top and centimeters on the bottom, and then you can do 100,000 centimeters. I don't know, something like this. But see, I need your math to look like that, the way it looks like when
you're writing it out.
Exactly, because otherwise I just can't follow you. There's another thing. I
understand.
All right, other things. So Evelina, you're going to get a bad grade on this, okay? However, because it's your first time submitting to me, I'm willing to take pity on you And if you submit it to me the right way, I'll give you some more points back so it doesn't hurt so much. But this,
Yeah, I
just
definitely will do that.
writing down the answers, I'm going to give you like 1 out of 5 for that. You need to show me the work with dimensional analysis. Basically, you need to do exactly what I did with these guys in office hours on Thursday. And luckily for you, that video is available for you to watch, and you can just copy me. So please don't go off on your own and do some wingnut stuff here. You gotta, you have to show me the work, okay? So this, Evelina, let's just say this is going to be so bad a grade that I want you, as soon as this class is over, to redo it the right way by hand or whatever and submit it to me, and I'll give you some good points for that, okay?
All right, thank you. I appreciate it.
You got it. You got it. Okay. And so, so I'm glad you mentioned that, Eva, because I'm not just talking to you. I'm talking to the other 28 people that are out there who aren't interacting with me live, you know? Okay. So now that that's aside, there's an issue with p squared equals a. Basically, what I'm doing now, Eva, is what I want to see. You copy everything I do. If I write it down, you write it down.
Okay.
There's a problem with the units of p squared equals a cubed. What is the problem? Someone, please.
They're not the same units?
Right. In this equation, it only works if the period is given in years and the distance, the semi-major axis, is given in astronomical units. So what are we going to do?
Convert.
What are we going to convert, Eva? Evelina?
The period to years, or the years to period, I mean.
We don't have the period will come out in years when we solve the equation.
Oh.
It's about what we are given and what we are trying to find. See, we're trying to find the period, right? So we want this. But that means we better have that. Do we have the average distance between the planet and the sun?
Yes.
What is it?
Is it that 112 times 1d 6 km?
10 to the 6 kilometers. Good. So Evelina, hiding in the background though you may be, you're going to help me do that. You're going to help me, even if it's tough, with dimensional analysis.
Oh, God.
You come on. See, this is what we need here. We can't just leave this up to Sage and Ryan. They're going to make it look too easy. You're going to have to struggle with me. So let's write down what we're trying to do, Evelina. Our first job is we need to convert the distance, and we have to convert the kilometers into AU. So did you take notes for our first, well, let's get real here for a second. Did you watch the first lecture? Let's start with that.
I did watch it. Did
you take notes on the first lecture?
Honestly, no.
Okay, now that's going to be a problem because I am assuming you do not have a photographic memory or something like that, right? So I need you to repeat for me the 4 steps of dimensional analysis. Now, these other folks, I'm hoping, did take some notes. They can do that for me. But I want to impress upon you, Eva, and I'm also talking to you other studio audience slackers who are watching this in your PJs upside down on your iPad in bed, okay? You should be taking notes. Everything I write down, you should write down, especially because I know you guys, you're not going to read the book. You're just not going to do that, okay? So this is your book, and you need to have it written down. Let's try Kathy. Kathy, did you watched the pre-recorded first lecture? Did you take notes?
Yes.
All right, that's good. Do you have the 4 steps of dimensional analysis?
Yes.
Okay, you're going to read them to Eva. You're not going anywhere, okay? You're singled out for extra harsh punishment today. Kathy, let's find read her the first step of dimensional analysis.
All right, write down the number to convert with its units.
Okay, Eva, what should I write down?
I would say the 112 and the 10 to the 6th power kilometers.
Yes, kilometers. Okay, with its units. So 112 million kilometers. Because remember, 6 zeros is a million. When I think math, so I think 112 million kilometers. But you can say 112 times 10 to the power of 6 kilometers or something like that. Kathy, what's step 2?
Multiply by a division bar.
All right, there's sort of no interpretation of that there, so we'll just put that in. So step 2 is already done for you, Eva. Now comes the important part, step 3. Kathy, read step 3.
Put the units in first to cancel out.
Okay, Eva, that's you. I need units top and I need units bottom. What do you think I should put?
You need the units, you said?
Yeah, units are like the little tags.
No, I don't know. I would,
Okay,
if
well-
I will guess that you would do the kilometers and the what you're trying to find, which is the P.
AU. Yeah, and you are correct.
I'm
Those are the two units you
Okay.
want to put in, but there's a trick here, Eva. One of them goes on top and one of them goes on bottom. You've got to figure out which it is.
I'll put the kilometers on top, bottom.
All right, remember, your motivation here as a character is the units have to go in such a way in which they cancel out. Now, the kilometers are on top because everything's on top unless it's specifically on the bottom. You can only kill kilometers if they're currently on top by putting kilometers in the bottom. And then you convert it into AUs on top. That's how we cancel out our kilometers. This is what dimensional analysis is. This is what I want to see on your homework. This is why you're going to need to redo it, okay? All right. Sorry, Kathy, could you read us the 4th step, please?
Yeah, plug in the numbers using conversion factors.
Okay, so now, Eva, your job is to give me a number top and a number bottom. Aren't you glad you showed up live to class today? This must be a
So
very
glad.
wonderful experience
Excited.
for you. Finally getting to
Ecstatic.
Okay, so
Uh,
all right, take a deep breath. Breathe in the paper bag, okay? Breathe into the paper
so I
bag.
put the 112 on the bottom, next to the kilometers, and then
What? So the 112 is what we're trying to convert. Here you need a conversion factor. So this is where you would go into your notes. Whoops. You would go into your notes. Let's see what we have here instead. So if you don't have notes, you could go into my crappy versions of the lecture notes and you could click on, I don't know, numbers in the nighttime sky. Unfortunately, this dumb thing makes you want to download it, which is really freaking lame. But, you know, Blackboard sucks. All right, so here we go. And we click on this. And now we look for our conversion factor. Oh, look, I use some nice equation editors for mine. So here's your conversion factor right here. 1 AU is equal to 150 million kilometers. So now your job, Eva, is to put those numbers into the slots in the proper positions. So what do you want me to put on top and what do you want me to put on bottom?
so wait, go back to it's 150.
Not just 150, it's 150 times 10 to the 6, right? You don't want to forget about
that's what I
those
didn't
6 zeros. Yeah. Keep going.
So the one of them is 1 AU equals 150 times 10 to the 6th power. Okay.
Cool.
All right. So to plug it in now.
Yep. Which number goes on top and which goes on bottom? Take a guess.
I'll put the 1 in the top.
That's right, because it's 1 AU.
Yeah.
And on the
And
bottom?
then the 150 in the bottom. The 150 to the times 10 to the 6th power.
Good. Now you're talking the way I want you to talk. 150 times 10 to the 6th power. Good. Okay, and now take your Casio calculator, which I'm sure you have, Eva. I'm sure you have your Casio calculator. If you didn't, that would just be, I couldn't even imagine. Okay. And now we're going to punch them in, right? We don't really need to multiply by 1. We can just divide them. So we do 112 exp6 divided by, whoops. I just had a glitch in the matrix there. Hold on. 112 exp6 divide by 150 exp6 and equals. What do you get?
I don't have it.
You and me are fighting now, okay? You
No,
doing all
literally, no. I'm warming up. This is a tryout.
okay.
After this, it won't happen again.
Okay, all right. So let me tell you, I'm reading into a crystal ball what's going to happen to you in your future. Class is going to end.
I'm gonna ace this class.
You're going to
That's
ace
what
this.
I'm gonna-
You can ace this class, but you need to get one of these puppies, a Casio FX260 Solar. You can get it at Walmart for $8. Sage,
Okay.
Sage got his on Amazon. Don't do that. You don't have enough time for that. Ryan, where'd you get yours? Ryan Dick, where'd you get yours? Ryan Spaveld.
To be honest, I got mine off Amazon too, so.
Oh,
Walmart,
how much did you pay, Ryan? At
like
Walmart.
$8.
$8. You're going to go to Walmart today and you're going to buy this for $8. You don't have time for Jeff Bezos to send this through the interwebs, okay?
I will.
All right, you need to get this today. So that, because remember, I gave you an amazing opportunity to fix your first homework, right?
You did. You
And
did.
so you can't do it without this. All right. Anyways, so Kathy, what did you get when you plugged it in?
I got 0.746 repeating.
Okay, well, can you round
No,
that
but-
up in a tasteful way for me?
Yeah, 7.46
No,
times.
no.
What?
No. You don't need scientific notation for this.
Okay,
You just need to round it.
just round. Do you want 3 decimals?
How about 2?
2.75.
Remember, we always put our leading zero out.
0.75 AU.
Minutes AU. That's right. Oh, God, this is going to be a long day. All right, so now we succeeded in fucking converting a little tiny number into AU. All right. Now what are we going to do? I'm just talking to anyone who cares or knows.
Just plug that into the problem.
Yeah, okay. So we
For
want to
A?
plug this in for A, right? This is equal to A. Now, we've got a problem right now, which is there's a square stuck to our P. I don't want no square stuck to my P. I want to get rid of that square. So I'm going to take the square root of both sides. Remember that the square root of P squared, that's just P. That's what I want, right? But I have to square root the other side too. So now I have the square root of A cubed. But that's cool because I know what my A is, so I'll just plug that in. That's the square root of 0.75 cubed. All right, now it's time to learn how to do that in your calculator. Eva, one of the reasons I'm getting the willies here is because I'm training these people each day on how to punch new buttons, and you need to punch with me or you're not going to get the training. So you better have a photographic memory.
Understood.
You got to look real carefully at what I'm doing here now, okay? Or
Okay.
watch this later or something. Meet around 65. That seems to be pretty good. Okay. So let's take a look at some keys. I need a pokey pointy thing. Okay. The keys that we're going to use for Kepler's laws is there's your x square, and there in orange is your square root. And up here in orange, some gick there. What is that gick? Some dry erase marker. Okay. Above the plus minus key, I've got the cube root. And above the backspace key, that's like a little delete key, you have x cubed. So what we're going to do is we're going to cube the 0.75, and then we're going to square root it. So watch my moves and follow, punch after me. 0.75. First, we're going to cube it. So shift cube. You should see that number. And now we're going to square root it. So shift square root. Kathy, what do you want me to round that to?
0.65.
Now you're talking turkey. And what units do we get there?
Six.
Oh, sorry. Remember, this is a magical formula. The units just kind of magically transform from astronomical units into
Is it the kilometer? No.
P is a period. It's a unit of time.
Oh, P. It's the unit of time. What?
I mean, like, if P is a period is how long it takes a planet to go
Yeah.
around the sun. So you can't measure how long in all right, that's not sounding right. You can't measure how long does it take to go around the sun in kilometers because I'm looking for units of time. Units of time would be like fortnight.
Hours, days.
Hours, days, yeah. But only one of these is the proper unit. To do that, you have to look at your notes. What do your notes say?
Hold on. 1 second.
See, this is why we take the notes.
Years.
Years. So this is 0.65 years. All right. That's part of our problem. That was honestly the hard part. Okay, now we're going to find the perihelion and the aphelion distances. Do you have all this down, everyone? I need to erase and move. Kathy, did you have time to write this? All right. Eva, I hope you got that too.
Yes, I do.
All right, good. You know to write it all down now. Okay, so now let's do the perihelion distance and the aphelion distance. To get the perihelion distance, we have to do A times 1 minus E. Now, we could use A either in kilometers or in astronomical units, but it's much more elegant to work in astronomical units. So we'll put in 0.75 AU. The eccentricity is 0.3. That's your E. 1 minus 0.3, close parentheses, equals. All right, let me show you the right way to punch this, okay? But-a-doo-doo. Okay, I'm going to make use of my parenthesis keys here to punch it in elegantly, and I'd like you to get some good habits now. So let's start by doing 0.75 times, open parenthesis, 1 minus 0.3. Let's close the parentheses. That does the parentheses. And then we hit equals to finish the job. Sage, what should I round this to?
.53
Units?
AU.
Very good. And that's because eccentricity has no units, so it's still AU. It's a distance.
Okay.
So 0.53 AU is our perihelion distance. And now we'll do our aphelion distance, A times 1 plus E, 0.75 AU times 1 plus 0.3. Okay, guys, punch them up for me. I don't want to have to show you every time. What do you get?
About 0.98, excuse me,
And the units?
AU.
Did you round proper?
I think so. I got 0.975.
Oh, okay, good. All right. So 0. Nice. That takes care of question 53. That was a little slow, partly because we hadn't done that before, partly because Eva's still kind of new to the class and was still practicing dimensional analysis. I do like it when you guys show up to live lecture because I can kind of force you to try. I'm erasing this, and then Ian's going to read me the last one. I'm erasing now. Ryan Spavel, are you cool? All right.
This is homework 2, right? I have to open up the PDF.
Yeah. And we just did 53. I think the last one is maybe 54. These weren't supposed to be long problems, but you know how it goes.
Yeah, 54. Okay, 54 says meridian crossings of the moon and Phobos.
What? From chapter 3?
That, I think so.
Wait, am I
I
tripping here?
was looking at chapter S1. Okay, I'm sorry about that.
Okay.
Okay.
Wow. Although that's, honestly, that's got me thinking now. I kind of want to try that problem. Never mind. Let's try 54.
54 is Halley orbit. So Halley's comet orbits the sun every 76.0 years and has an orbital eccentricity of 0.97. A is find its average distance from the sun. the semi-major axis.
I'm sorry, did you say 0.97?
Yes.
Okay. Once again, I'm extracting the givens before I start the problem. Ian, you've had training in my solar system course, so let me focus a bit on Kathy and Sage. Sage, you're an old hand at solving problems. What do you think I should do here?
We are looking for its perihelion and aphelion, correct?
I'm sorry, can you read me the problem one last time, Ian? No, I got confused too.
A is find its semi-major axis, the average distance from the sun.
All right, so let's start there.
And then B is peri and aphelion. So
Sage, do you know how I'm going to find the semi-major axis?
With the perihelion and aphelion?
Well, we weren't really given perihelion and aphelion, were we?
No,
were
we
given the
weren't.
period
That's
and the
why I'm
axis.
confused why it's that way. Could you multiply the period by the eccentricity? You get it? For the
That would be a bad idea. You
Yeah,
could do that, but you wouldn't really get much from that.
yeah.
So I think the problem is, Sage, that you might be, this is a failure not of mathematics so much, but of vocabulary and of understanding. Let's
Yeah.
have a talk, shall we? I think it's time that we all had a little talk about A, the semi-major axis, all right? Let me- Yeah, there's a reason why you're confused, and I know what it is.
Yeah.
So let's take a trip back here and let's look at an ellipse as I introduced it to you. Here's a picture of an ellipse, and I've got something confusing to say, so I need you all to pay close attention. I want you to notice that A is originally defined as the semi-major axis. That is the distance from the center to the edge of the ellipse, okay? But what makes A weird is A really doesn't at first seem to have anything to do with the planet and the sun. The reason being that the sun, according to Kepler, the sun is at a focus point over here, and the planet is on the ellipse, maybe over here. And thus, the distance from the planet to the sun is like that. Now, the blue arrow at first does not seem to have anything to do with the red arrow. The red arrow is the semi-major axis. But suppose, for instance, you wanted to find the average distance between the planet and the sun. Well, you'd have to look at a picture kind of like this, right? What you'd have to do is you'd have to measure the distance between the planet and the sun a whole bunch of times, like here and here and here and here. And you'd have to take the average of all of those distances. But then you'd realize that this isn't even good enough, because that's the average of these 12 points, A, B, C, D, all the way to L. But what about this distance here? Don't we have to account for that? If we really want to know the average distance between the planet and the sun, we are going to have to find the distance between the planet and the sun kind of like an infinite number of times. And then we're going to have to take the average of those infinity distances between the planet and the sun. And egads, holy shit, there's a mathematics that can do such a thing. It's called calculus. Calculus is capable of taking the average of an infinite number of distances between the planet and the sun, because it's magic and you could never understand this. But let me tell you something. If you did understand this, and if you did this, you would discover that by the magic of mathematics, once you averaged all of the distances between the planet and the sun, it would just so happen that the average distance between the planet and the sun would turn out to be A, the semi-major axis of orbit. And you can almost kind of see that, because think about it. If you took the average distance between the perihelion and the aphelion, you would add both of them together, and then you would divide by 2, right? And when you divide it by 2,
okay.
but here's the problem, okay? From now, let me get out of here. From now on in this class, A, the letter A, it means 2 totally different things that are the same thing. And that's kind of confusing for students. it means A is both the
Uh-oh.
semi-major axis of the ellipse, which is a geometrical property of ellipse, but A is also the average distance between the sun and the planet. So now that you understand all that bull crap, Sage, what am I going to do if I've been given a period and they want me to find the semi-major axis of Halley's Comet's orbit?
You could square it, take it to the third root.
In other words, we could use Kepler's harmonic law.
Yeah.
We could use p squared equals a cubed. Except now we're looking for a, and we've been given p. So really what we'd want to do is rewrite it in the reverse direction. A cubed is equal to p squared. Now, Sage, I'd imagine that a savvy mathematician such yourself would know how we could destroy this cube and simply solve for a. What do we do to get rid of a cube?
Cube root.
Cube root both sides.
Yes.
So if I cube root all of this stuff, the cube root of a will become a, but on this side, I'll end up with the cube root of p squared. How are our units looking, buddy?
We're gonna go from a year to kilometers or AU.
Yeah, what's the conversion from years to kilometers? I forgot.
Yeah, I don't think there is one.
Yeah, I don't think that makes sense. I was gonna see if you went looking for one. I was gonna have a chuckle at your expense. But I guess yeah. Okay. So what are the units of P and A supposed to be then?
Years in AU.
Okay. So what's my problem then?
Not having a conversion factor. Or
Ian, can you explain this?
yeah.
Let's ask a vet.
I mean, I may be wrong here, but you said this earlier. It kind of just converts when you put it in the harmonic law, right?
Okay, all right. There's converting units, and then there's plugging into equations. Yeah, in p squared equals a cubed, if you plug in a p in years, it magically comes out in AUs. Okay, if I had to write the formula the real proper way, I would write p squared is equal to a cubed times years squared per astronomical units cubed. But I just happen to know that nobody wants to look at that shit, and it makes it more complicated. So instead what you do is you forget about the units and you tell people that it's magic, okay? So this formula is a magic formula. You don't have to convert anything, Sage. You already have the proper units. That's what I was trying to get you to say. Right? Because your P is already in years. So what am I doing then, Sage? I'm lost in the sauce here.
So we would take 76 and we would square it and cube root it.
Sounds like a great idea. Let's do that. This time we'll use the other two buttons on our calculator. We'll do this in reverse. Okay. So we'll do 76. First, we have to just square it. So we'll hit that button, doink. You get 5776. And now we're getting shift, and then we cube root, shift, cube root. All right. So what should I write for my final answer?
17.94.
Wow, 4 significant figures.
Or
Totally cannot justify by your givens.
yeah, 17 AU. Sorry.
Well, you've actually got 76.0. How many sig figs is that?
That's 3, but the eccentricity is 2. Oh, the eccentricity.
Well, we didn't use the eccentricity in this calculation.
Yeah. Okay. So you could get away with 17.9 then.
You really could, but let's just make it 18 anyways, because it's funny. Okay. Okay. It could have been 17.9, but now that you know that, I'm cool with 18. Okay. All right.
Okay. I know I should have this down by now, and normally I do. I don't usually mess up on the calculator, but I cannot get it to say 17 something.
Sure. Can we just, why don't we watch again? I'm sure this, Ian, if you're having trouble, there's got to be other people as well. Okay. 76, you got that? Just hit the square. Bam.
I was confusing myself, and I was hitting shift and then square because I was like, oh,
That would be
yeah,
the square root. I figured
that-
something like that. All right. All right, problem solved. Now we have to get the, that's A. For B, we have to find the perihelion and aphelion. Sage, walk me through it.
So the formula for the perihelion is going to be on another paper. I believe that's A1 minus B.
A times 1 minus E.
Yeah.
Same thing, I guess. What's my A?
18.
18 AU, you says.
AU, yes. Says that.
Okay, now what do I put in?
1 minus, what do we have for E? 0.97. 0.97.
Okay. I showed you guys how to type that in last problem, so go ahead and do that. Tell me what you get. Give me some reasonable sig figs. Sorry?
0.54.
Units?
AU?
That's right.
Cool.
0.54 AU. Now I've got to do the aphelion, but I've run out of board space. So I'm going to come back up here. Aphelion is A times 1 plus E, which is 18 AU. Times 1 plus 0.97. Oh, I'm gonna really regret this.
I got 35.5 rounded, and that would be AU, if that's what you're.
Too many sig figs.
Okay, 35 AU.
Shitty
Or I guess
rounding.
you could say 36 AU then.
Yeah. What planet's orbit is closest to the perihelion point? Does anyone remember from my lecture? What planet's orbit is closest to half an AU?
It's
Is
not
it-
Mars.
Venus?
Venus or Mercury? Mercury's 0.4, Venus is 0.7 something. Somewhere between Mercury and Venus. What orbit is closest to 36 AU?
Pluto.
Yeah.
Yeah.
So Ryan, let's think about this from the perspective of Kepler's laws for a second. If we were to, well, let's look at the, I'll use comment. I bet there's a sweet, I'm pretty sure there's a sweet diagram of this on the Wikipedia page. You can learn so much on Wikipedia. It's just amazing. I love it so much. Here's a picture of Halley's Comet. It was around when I was a kid, but don't worry. I'll get another chance to see it when I'm like 105, so no big deal. But it came around in the 80s. I was really young, so I kind of just barely remember it, but it was a big deal. Its orbit is insane. By the way, this diagram shows it obeying Kepler's second law of planetary motion as well. Notice it gets a lot faster when it's close to the sun. It comes interior to the orbit of Venus, so it crosses past Earth, but then it goes way out past Neptune's orbit near Pluto. But because it's traveling equal areas and equal times, it travels really slowly and spends a ton of time at the edge of the solar system. And then it just comes zipping through the inner solar system in a period of about 2 months or so. So you only have a couple months you can actually see it. It's the orbits of comets are highly eccentric. That's why they're quite interesting from an astronomical point of view. They're not circularized. Let's see. 1986 was the last time. So the next time will be, what was it? I just had it there, 2061. So that's, geez, 40 years from now, right? Did I get that right? Yeah. So maybe I will, I'm sorry, I won't be 105. I'll be, I don't want to tell you what I'm going to be, but I'm going to be a geriatric, okay? I'm going to be an octogenarian. I'm going to be even older than I am now, if you can believe that. Okay, that's our homework, and suffer and succotash. I've screwed up, and I did not get far enough into our lecture for us to do homework number 3. Now, I gotta make a decision about what I want to do about that. Gotta be careful here. One decision is that we just don't do the homework next class and we wait, which is probably the easiest path of least resistance for all of us. I do like us to do a problem set every class, so I could make one up. Oh, wasn't there a homework problem that we didn't do? We chopped one off. Was this the class where we did that? I can't remember which class did what. No, we did that homework problem today. Never mind. I'm thinking of my 1010 course. Okay, I have to make a decision right now. So I am not going to have homework number 3. We're not going to do that on Thursday, okay? Because we're just not ready for it yet. So we're going to skip. I don't know. It's summertime. Screw it. Let's just not do homework next class, okay? So you're going to have the homework for today, the lab for today, and on Thursday we will do a lab, but Thursday we'll meet at 12. That way we can sleep in a little bit. Does anyone object to this plan? Does anyone think this is a bad plan? I didn't think so. I didn't think so at all. Okay. So since we're not ready for the homework anyways, I could manufacture a new homework for you, but I think I'm just going to let you guys take it easy and we'll just do lecture and lab on Thursday. That sounds great. Okay. So now it is time for lab.
Sorry, I have a question.
Evelina, hit me. Evelina.
Just can you just clarify again what needs to be handed in for next class? So just no homework, but the labs are due?
Yes, so understood. I'm being confusing. Can I erase this, everyone?
Yes.
Let me kind of draw it out for you. You can copy this down, okay? So this week, Evelina, we had class on Tuesday today, and we have class on Thursday. And today we did homework number 2, and we're about to do lab number 3, correct? We were supposed to do on Thursday homework number 3 and lab number 4, but we are not prepared to do homework 3, and we're like almost a lecture behind, which, by the way, this isn't the first time that's happened in this class. This happens a lot. So what I decided just now is going to be due. Remember, the due date is Sunday night at 11 p.m., correct? I'm not going to grade this stuff tonight. I'm going to do other stupid things. So what I'm going to do is I'm going to grade homework 2, lab 3 and lab 4 Sunday at 11 p.m. Does that make sense?
Yep, thank you.
And we'll kick homework 3 to next Tuesday. All right. Evelina, that was a good question to ask. That way I'm being very explicit, okay? Okay. I'm going to pause the video for a second as I transition the computer to the lab section. Today's lab is short. Let's not take a break. Let's just crash through it, okay? Let me, how many of you have a printout of that page here?
I'm looking for it right now. It's page 5.5, correct?
Yeah, it's the 5th page in that handout.
Okay.
You could redraw it, I suppose, if you needed to, because it's quite simple. These two focus points, I think, are 12 centimeters apart. I'll measure that in just a moment.
I need to see about printing mine out. I've been over this with you. It's a really weird situation for me right now. You can go ahead and start because I'll still follow along. I have my same lab from last semester, so I can look at that if I need
Ian,
to fill.
It's actually, it's so simple. And don't forget, buddy, look what I did for everyone. I provided a pre-drawn ellipse. I really should not have done this.
It's just like the printer situation. Like, can I write on it with a PDF editor? Is that okay?
I think you can.
Okay.
I would
then
like you to
I'll
try to
just
do. I would like you to try to do some measurements. You know, one of the ideas is that I'm not making you do that much. I would like you to do some measurements here. Hold on. It takes a little while to do Blackboard. Come on, you bastard. So I provided an ellipse drawing. So I kind of did this in a previous year and I uploaded it because not everyone had their stuff together. So you could try to rotate it and just do something, okay? Okay.
At the very least, I think I have done this last semester too, so I'm not completely,
Lost, right?
getting nothing out of it.
And you can, hold on. Hold on, guys. I've got a Japanese screen on my damn thing here. I love teaching from home. Okay, let's see. We got our paper, we got some tools, we got a ruler, we got those thumbtacks. Now, any one of you that actually pull off doing this with the cardboard and thumbtacks, I'm going to award you the Golden Cookie Award for bravery and excellence, and I'm going to be very impressed with you. It's not very difficult. Let me help with the setup here. I'm still recording. Oh, I meant to pause that, but I guess I forgot. Okay, let's see if we can't use my phone. Let's make sure that all of my other tabs are closed so I don't do anything embarrassing during my lectures. That's just a picture of me with my friends. That's not too incriminating. Okay, so you never know what's going to be on this thing when you're teaching class. Okay, so let's see here. We're going to share. The goal of today's lab is to get our fingers dirty and make a scale model of a Keplerian elliptical orbit. Okay, that's not as hard as it sounds. Let me start by sharing the screen to my iPhone. And I will make sure my Wi-Fi is on. Okay. And then, so I do this, screen mirror, zoom. Okay, here we go. It takes a second here. Okay, there we go. Let me take portrait lock off and let's go to camera. Okay, so tools of the trade. Hold on. Trying to flip this so my. Oh, there it goes. All right, how's that looking? Okay. All right. So tricks of the trade here. I've got some thumbtacks. I've got a string that's been tied into a loop. Now let's think about this. The loop of this string has been tied to about, somewhere between 14 and 15 centimeters. So I'm guessing the original string was maybe twice as long, maybe almost 30 centimeters. And then it was tied with a little knot. I don't know if you guys have the knot skills to tie some string into a little knot, but I bet you could figure it out. Okay. I have a crappy piece of cardboard and a ruler. That's all we really need. Here's my paper. I do need a pencil. Hopefully I've got one of those. Sharpen it up. Sharp pencils, sharp minds, right? Okay. Now, at the top of our page, we will put our names. This is astronomy 1020. Wow, I'm all kinds of dumb today. Let's see here. That's astronomy 1020. And this is lab number 3, planetary orbits. Ooh, okay. What we're going to do is we're going to take out 2 thumbtacks. I will choose green for science. Okay. And I will poke the 2 thumbtacks into the focus points, which I mentioned before are 12 centimeters apart. How many of you are actually trying to pull this off? All right. Well, we got 1 person anyways. Anyone else? I probably should have warned you about this last time. Okay, so let's take the loop of string. Now watch, I'm going to put it underneath against the metal part of the thumbtacks, okay? I'll use the knot here. I'm going to put the pencil. I'm trying to hold this steady with one hand as I do this, so put the pencil in tight. With the fudge. And now look, I made a perfect, beautiful little ellipse here. You guys see that? It's kind of egg-shaped. Okay, let's remove that. Everyone can have slightly different size ellipses. That'll depend upon the length of your string, okay? All right, so here's my ellipse. And what I'm going to do is I'm going to kind of label a few of the parts of the ellipse. I think what I need for this is I need to use my roll of tape, okay? I might have to go vertical on this. It's not quite as pleasant. No, that's not going to work. Hold on, I might have a tool here. 1 second. All right, I think if I do this, hold on, sorry, I can clamp. Okay, cool. Cool. Look at that. See, how cool am I? Experimental science at work. Here we go. It'd be cool if I could just get a little, let me just prop this up on a couple of cue cards. I bet if I did this and this, I could even get a slight angle on it. Okay. Oh, shit. Okay. Sorry. Yes. Oops. No. All right, that's good, but it. Haha. All right. Sorry, that took a minute to figure out. Focus. Can I focus that? There we go. Okay, cool. Sorry about that nonsense. We are going to make a scale model of a planetary orbit in which 1 AU is equal to 1 centimeter on the page. And I want to do this such that the tolerance of our measurements is plus or minus the nearest 1/10 of a centimeter. So all of our measurements should be done to the nearest 1/10 of a centimeter. Okay, first thing I want to do is I want to draw on my major axis. So I'm going to make a careful line connecting the 2 focus points, but I shall go no farther than that. This is the major axis, and you can see down here, I'm responsible to measure that. So I will measure it. What would you guys say to the nearest 1/10 of a centimeter? I'd like your class participation. What would you say is my semi-major axis there? Sorry, that's my major axis, pardon. What's that measurement?
I mean, you could round up to about 18 centimeters.
No, you fucking couldn't, because
Okay.
I told you the tolerances
Sorry,
of all of your measurements would be the nearest 1/10 of a centimeter, right?
my mistake. My mistake.
That's okay. I wanted to make that point dramatically, Ian.
Yes. So that would be 17.8.
Yeah, you are clearly capable of discriminating that it's the 17.8, not the 17.9, nor the 17.7.
Yeah.
That's what a tolerance of plus or minus 1/10 of a centimeter means. It means to the nearest millimeter. Okay, so let's write that down, provided that was your measurement. Here, 17.8 centimeters. Okay, now, oh, sorry. We're gonna do this as a scale model, right? So let's be cutesy and let's call it AU, as if it was in space, okay? Because 1 centimeter is equal to 1 AU. All right, now in our homeworks today, we used a formula to calculate perihelion and aphelion. Sorry about the lag here. I can see there's a little bit of lag. What are we going to do here? In this case, we're supposed to measure. Well, I guess we should probably figure out where our minor axis is. Let's find the center of the ellipse first. So I'll take a measurement. Let's see, what is half of 17.8? Let's ask a math expert. What's half of 17.8?
8.9.
8.9 says resident math expert. Now watch how I do this, guys. There's a trick to making these. I'm going to line up my 0. Notice I'm lining up my 0 real careful. As careful as can be. And then I'm going to go to 8.9. And I'm going to make a little vertical tick here. That's, my daddy was a carpenter. This is how he would do it. He makes a little tick mark right along the same direction as it, and then you can mark that as a midpoint. Okay, that's the center of your ellipse. Now, let's go ahead and let's draw in our minor axis. Okay. The minor axis should be perpendicular to the major axis. I use a little trick. I kind of line up. Oh, why is it? There we go. Sorry, it's frozen for a second. I use that, see how I'm lining up the line with the 5, and I'm going to try to draw in my minor axis as perpendicular as can be. I guess that looks not too shabby. It's a little wiggy wonky, but that's all right. Actually, it looks better in person than it does on the screen. Okay. Let's do some things here. Just like we did in our lecture today, let's label this the major axis. Up here, we'll label it the minor axis. This is the center, which in the lab session, they suggest we call the center C. I'll just kind of put it there, small c for center. Okay, let's also label a couple of other positions here. Let's make, the sun needs to be at one of the focus points. Now here's where I'm going to use one of my cutesy little circle makers, okay? Because I like to make it all cutesy sometimes. Let's put the sun right there at the center, centered on that focus point, okay? And let's label that as the sun. You can put some beams of light coming off it if you want. Make it look like a giant creepy eyeball or something. Okay, there we go. And now let's just put the planet somewhere randomly on the ellipse. Let's put it up here. This could be any old planet, could be Earth, could be Jupiter. Okay. There's my planet. Okay. Give it some stripes like it was the planet Jupiter. Okay, there we go. Now, one of our jobs is to, oh, I'm sorry, I want to label two other parts, and we'll do this kind of architecture style. X is the distance from the center of the sun to the center of the ellipse. So I'll put an X here, and I'll draw a line from there to there. So that's X. It goes from the center of the sun to the center of the ellipse. A is the semi-major axis. That's half of the major axis. So it should go from the edge of the ellipse to the center of the ellipse. See if you guys can do that. All right, first gig. We actually have to measure the perihelion distance off of the ellipse. Class, give me some good thoughts. How should I measure perihelion?
From you'd take the opposite side of the major axis from focal point 1 and measure to the sun.
Not exactly, Ryan.
Not exactly.
What does perihelion mean?
Oh, sorry about that. I was thinking aphelion for a second. You'd measure from focal point 2 to the end of the, from the sun to the very end of the major axis closest to it.
In other words, oops, sorry, things are weird. Whoa, what the hell is this? What? Ah. Okay. Sorry, Ryan, hold on. I'm having some difficulty with my phone crapola here. Oh, shoot. I don't think it likes when that metal thing comes down on my phone. It gets irritated on. Sorry, guys. This thing is jank. I gotta rotate and flip. Flip. Sorry. There's like, I know this seems horribly inefficient, but this is the best way. I don't understand why it's not flipping. I need to. Okay, I'm doing something wrong here. There we go. Jesus Louises. Wow. Note to self, don't undo that again. Sorry, friends. Okay, this is our perihelion point. Let's mark it. I'm so sorry about all that mischief. It's this new phone. I'm trying to figure out. I got this phone like a week ago, and I'm still figuring out how to use it the best as possible. Over here, focus. We can measure our aphelion. Let's label that point. All right. Okay. Ryan had the right idea. We'll go from the center of the sun to perihelion, and we'll measure that to the nearest 1/10 of a centimeter. I go through great pains. Now we only need to go to the nearest 1/10 of a centimeter. What do we think, guys? This is sort of a judgment call, right?
2.9.
Okay, I'll mess with that. So for perihelion, we'll have 2.9 AM. Okay. Now, Ryan, tell them how we're going to do the aphelion. That's the aphelion point.
Are you still talking to me or are you talking to Brian Dick? Just
Oh,
to be clear.
Ryan Spaveled, I guess.
Okay. You would measure from the aphelion point to the center of the sun.
Right there. That's the aphelion distance. Good. I figured since you were understanding it, we'd just stay with you. Let's do a little zoom in there. This is so cool. It's like we're doing it in lab together. Okay, so what do you got?
14.8.
I'd say it's a little closer to 14.9. Whoa, hold on. Well, sorry. I would say it's closer to 14.9 personally.
Yeah, now I see it.
It's all right. It's a little messy because the way I made the dot. Your measurement was not unreasonable.
Do they have to add up to the major axis, or is that arbitrary?
I mean, in theory, they should, but guess what? This is because the tolerance of our measurements is plus or minus 1/10 of a centimeter.
I just wanted to make sure I wouldn't get anything wrong, just for syntax.
Right, but
Syntaxular.
Sage, that means as long as our measurements add up to within 1/10 of a centimeter. So do they add up to within 1/10 of a centimeter? That's how measurement works. So
that makes sense.
if we got 14.9 AU, then 14.9 plus 2.9. Oh, actually turns out to be exactly 17.8, doesn't it?
Yeah, that's why I was just being anal about
I wasn't trying to force it that way for a reason. I don't know.
No,
At the
yeah.
end of the day,
I just wanted
sorry. Measurement is an art form. It is a judgment call. The
Word.
skill of the measurer comes into play. That's the skill that is involved in experimental science, is how good can you choose the ultimately you are a human who has to interface with the measurement. You have to decide.
Mhm.
You have to be the decider in chief, as George W. Bush once said. Okay.
That totally makes sense. Just in terms of like topic questions, I wanted to know what the rule would be if there was one. So I'm glad I asked.
Even if we had chosen Ryan's decider in
Because
chief,
it's within that tolerance.
it was within the tolerance,
Yeah.
right? So it's fair because it means we've given ourselves a slop of 1/10 of a centimeter. Get out of here. This is what I'm worried about, okay? Let's just hope it stays PG-13, okay? All right, so, all right. Let's try to measure X next, okay? Before I get any embarrassing text messages. All right. So judgment call. Sage, you be the decider.
Let's go with 6.
However, if we are measuring to the nearest 1/10 of a centimeter, we would not just say 6, my mathematical
0.
friend. We would say 6.0. Now, that says to the viewer, I didn't just choose 6 the way that Ian tried to choose a number earlier. I was saying it's definitely not 6.1, nor is it 5.9. I'm telling you that I bothered checking to the nearest millimeter. Oh, and we're using AU. So
Cool.
now, let's have Kathy try her hand. We have to measure A using our measurement and judgment skills.
I would say about 9.0.
You'd say 9.0. So I think I'm following her too. She's saying, okay, the dot is there, but if you look at the curve, maybe you're suggesting that the curve kind of grazes 9.
Mhm.
Is that how you were thinking?
Yeah, and it's just looks more in the middle between
Yeah.
8.9 and 9.0.
Yeah. Okay. I like all your thoughts. Okay. So I like it. I think there's a fair judgment call to be made there. 0 AU. Okay, now we're almost done, kids. We have to calculate E and we have to calculate P for this hypothetical planetary orbit. What was the formula for eccentricity? Did I tell you about that? How do we calculate eccentricity?
Since we have A in the perihelion and aphelion, we could figure it out using one of those, couldn't we?
There's an even easier formula, which is the definition of eccentricity.
P
Look in your
squared equals
notes.
A cubed.
No. Does anyone else see it?
Oh yeah. There's no-
Isn't it X divided by A?
Very good. Who was that, by the way? I'm trying to learn everyone's voice.
Other Ryan?
Oh, other Ryan. Yeah, sorry. You're just off my screen, Ryan Dick, so I didn't see it. So yes, Ryan.
Hey, good.
Other Ryan, oops, sorry. That's why we use pencil. Okay. The eccentricity, the definition of it, like how it was defined, and this was a small detail that might have slipped the cracks, is X divided by A. Now, according to UCATS, Rx is 6.0 AU. RA is 9.0 AU. AU's cancel. Let's punch it. 6 divided by 9, I guess. How many sig figs should I keep?
Two.
2. And so how should I round it then? See, there's 2 on the top, there's 2 on the bottom, so we're going to keep 2.
6.7. 0.67.
Right. Any units?
No unit.
No units. Okay, good. So put that here. Notice that even a 67% eccentricity is kind of egg-shaped looking, right? All right. How about the period? How are we going to do that? How could I get the period?
P squared equals A cubed.
Beautiful. Let's write it down over here. P squared equals A cubed, okay? Now underneath that, let's write the P is equal to the square root of A cubed, because we have to, if you put the square on the other side, it becomes a square root. And that's equal to the square root of, I guess it's 9.0 cubed. So now we'll do that. 9.0. Now the cube is here, so I do shift cube. That's 729. So P is equal to the square root of 729. And oh, come on, get out of here. Okay. So shift and the square root key is here. Oh wow, it came out 2 sig figs, just like we like it. 27. What are the units? Hoop Sage.
Magic years.
Magic.
Or years, but converted magically.
Yeah, magically transformed into years. Very good. And this, my friends, is a model of a planetary orbit that uses all the things that we learned about today. And this is all I wanted us to do for lab today. There was another part to this lab that's really, really long, but I figured you've listened to me long enough. We'll take it easy, okay? Does everyone have all this? That drawing, the whole thing, I'm gonna look at it all. Right, Ryan Dick? I'm gonna check out your drawing. I'm gonna look at yours extra careful, won't I, Ryan?
Yep.
Now that I've seen you are a dishonest centimeters cheater, then I will be carefully examining your diagram for any signs of chicanery or tomfoolery. All right, so, all right, let's stop this before I get any embarrassing texts. Okay. And share. All right, how are we doing on time? 3:36? I got no problems with that. You guys got problems with that? Okay, didn't think so. All right. It actually is a little depressing that I'm well, in some sense it's nice because I won't have to wake up at 10 o'clock come Thursday, which that's good for me, okay? Same with you guys, although you may not be as much of a lazy degenerate as me. On the other hand, we do need training. It's not enough to just sit and listen. We have to do things with our hand. We have to punch things. We have to practice our vocabulary terms to learn. That's how you learn, with your hand, not with your eye, okay? So it's a little lame that we're not going to be doing a homework because each class you guys are going to become stronger and more interesting for me to talk to. However, next week's homework involves some Newtonian gravity stuff, which we just did not get to. And we're kind of in an awkward transition period. We're going from Kepler's laws to Newton's stuff. Had I been faster and more efficient today, that would have been cool. But in any case, I think it's okay. We'll skip the homework. We'll just meet for lecture and lab on Thursday. And then back to business next Tuesday. We'll get back to the homework, okay? All right. And I'm sure you guys don't mind. So you'll turn this homework into me now. I'm going to try to finish grading the other three. Please get the homework in that we did today as well. People like Kathy and Ian, you're going to have to go back and watch those 3 questions, right? Okay. You could watch those 3 questions from the previous semester if you don't want to wait. Because this video is about 4 or 5 hours long, it's going to take a couple hours to render. So right now, you guys are sitting in front of your computers and you're all kind of hopped up and ready to go, right? So I did these 3 problems. Let me send you the link. Share.
I was going to say, where can I find that?
Okay, let's see. if we can find that from last semester. In the announcements, I have the old videos hidden back there underneath things. So we have to be careful because sometimes I do different homeworks for the spring semester than the summer semester, but the beginning ones are certainly the same. So let's go back here to homework number 2. Should be about the same. Hopefully this was a good one and not a bad one. So there's the one. Like copy video URL. Let's go to chat. Paste. Can you guys see that? This one probably came at the end here. Why don't you guys let me find the timestamp for you? This is just so that Ian and Kathy can get going on the first 3 problems and not waste any time, because otherwise we'll be waiting for hours. It probably came in like about an hour and a half in. There we go. I'm probably being long-winded, as I frequently am. I can see it. I can see it on the board. Yep. There we go.
I love that that one woman was straight up steaming feathers.
Was doing what?
She had like a whole wardrobe going on. It looked like she was in set or something. I lived.
Oh,
There
I don't know.
were-
People do it.
black and red like show feathers. It was great.
That's great. Yeah, people do it. One kid in my class one year, he lived on a farm and he just had a rooster and he would hang out with the rooster in the screen during the live shows. I loved that guy. That made it so much fun. So show me all of your ridiculous animals. Okay, so you've got the URL. The timestamp is right like I suggested, right around 1:30. Okay, 1:30:42. So to do the first 3 problems, Ian and Kathy, that might be nice for you just to kind of crank them out right now, right? As opposed to waiting around for hours. So remember, you need to get, and I'll write them down in a second. Let's just verify the same. Yeah, 59, 41, and 43 from chapter 2 and S1. And you've already got the other 2 there. So you guys get on that right away. I'm going to exit here. And I'll see you guys. We're going to meet Thursday at noon, not at 10, correct? All right. I'll probably have to send a note to everyone about that.
Are we also submitting lab 3?
Yeah, do
Or
that.
are we doing- okay.
You know how to do that, right? Okay. All right, guys. Take care of yourselves. I'll see you on Thursday. Good hangs as always, okay?
Have a
Yeah,
good week.
Professor, if you want, I'll show all my animals next week.
Oh yeah, you live on a farm, right, Ryan?
Yeah.
Yeah, maybe we should, there used to be a way to give other participants access to share their video, but I think CCRI took that away from me when I merged my account with theirs. But that would have been so cool if you could, like, the way I send it to my phone, if we could, I don't know how you're gonna do that because they're out in the barn, right?
Yeah, and it's not far. It's literally just a walk.
Well, look, if you can figure out how to do it, maybe you could just log into the Zoom from your phone. I totally
Yeah,
wanna
that's
see
what I
all
was
your-
probably gonna try to do.
I want to see all
That's
your
what I was gonna
crazy.
do.
Show me the goats, the horses, whatever you got, chickens. I'll look at all of it. Okay.
All right.
All right. We definitely want to see that. I need this city slicker here needs some rural fantasy life. Okay. All right. So I'll see you guys on Thursday at noon. Over and out. Bye.
See ya.